Welcome back, everyone. We are here for day 3 of the Go Cloud Careers completely free Azure Solutions Architect Expert Bootcamp to prepare you for the AZ305, the Azure Solutions Architect Expert certification. So, this is day 3. On the first day, we talked about connecting to the cloud as well as the way the cloud was organized. Yesterday, we talked about compute and we talked about databases to a degree. We've got a whole lot of fun stuff to talk about today, so let me know that you're here. Let me know where you're actually at. I always find it interesting to see where everybody's from. I know I'm here in South Florida today, but I know we've got a pretty big international audience, and I love seeing it. So, where are you from? Cyprus, Texas. I love that. I'd like some Cyprus, the country as well. Yesel in Orlando, fantastic. Yogita, what a great name over there in India. Yogi myself and a yoga instructor for the practice yoga every day for the last 18 years. Anything with that kind of name to me is super cool. Chow's over there in Dallas. JDF Trades in Jamaica, one of my favorite places in the entire world. Go there all the time. And Jim over there in Indiana. It's good to see you again, Jim. So we're going to get into some more about databases. And then after that, we're going to get into my favorite topic, which is networking, which is really where my background comes from. So we're going to have lots and lots and lots of fun today. If you've not seen day 1 or day 2, don't worry. You can go back and watch them. They're sitting on our YouTube channel. So let me tell you about a few things to remember. We're going to focus on making sure you understand this technology. This is the first week. We're going to be going over the Azure fundamentals this week. Next week, we're going to be going more into that solutions architect kind of expert training, but we need to make sure everybody's level set. We want to focus all this time on making sure you learn the technology, because I interview people every day and certify people every day, and I ask them questions and they don't know how to answer them. Now, they may know how to click a few boxes on the management console, but nobody gets through an interview without understanding the technology and being able to explain it. So we're focused more on that here, especially as cloud architects, solutions architects, enterprise architects, AI architects, which is our community. We don't configure technology anyway, but still love you to get hands-on. So we've got a bunch of free Azure Lab demonstrations for you to go through. Go do this on your own time. But the real key to being able to do anything more than admin level is understanding the tech. What is the tech? How does the tech work? How do we put the pieces and parts together? Why do we use it? What's its impact on the business? So that's our focus for this, because we've interviewed thousands of certified people over the years, and very few can pass the interview because they don't understand the underlying tech. So we want to make sure you do. So that's our focus. But nonetheless, please get those free lab demonstrations, and please do them at a time that's convenient for you. Also wanted to let you know that Thursday, almost every Thursday, we have a how to become a cloud architect and get your first job. This is a completely free webinar. We will go over the architect role. We'll talk about what architects do. We will talk about the right skills that you need to be an architect, which are going to be different than you think they are. I promise you that, unless you've actually worked as an architect. And it's all going to be free. So come join us. It'll be on Zoom, and there'll be all these kind of great things that you can do. Now, please make sure you check out the description of this video. In this video, we've got free ebooks that we wrote on how to pass an interview. And if it's not, my team will pop it in there. Ebooks on how to become a cloud architect or an enterprise architect or an AI architect, and so many other free things that we've put out there to help you with your career. So go out there and grab them. They're all completely free. So we're going to get back to the content. But before we do, give me a hashtag. Give me a hashtag AZ305 or a hashtag Azure Solutions Architect Expert. It's your choice. But I come from the medical world, and we want to know people who are oriented towards person, place, and time. So that'll give me that information that you are here and you're ready to go, because I want to go. I just want to make sure you're all here and ready. There may be some goofiness in the chat box today. If you are having the same issue, we completely understand. Our team's trying to post to it, and some messages are going through and some are not. So if not, please try again. We'll get there. So we're going to begin with caching. So what is caching when it comes to databases, and why might we use it? So I'm going to whiteboard it out for you. We're going to start with caching, then we'll get into some other things. At some point today, we'll talk about queuing. We'll also talk about read replicas and scaling. But right now, we're just talking about caching. And the reason is we've covered relational databases and NoSQL databases. And things like read replicas are only for scaling relational databases, but caching is for everything. So we're going to start with caching. So what is caching? Caching is to place certain information in easy access memory. And by placing information in easy access memory, you can get it faster and you can offload the work to the server. So that's why we would use caching. There's a lot of uses of caching. So let me kind of show you what it is. We'll do my favorite thing, which is whiteboard it out. And then after we whiteboard it out, we'll continue with the caching topic and we'll talk about the types of caches, etc. But you have to understand what is caching. So let's say we have a database here. Here is our database server. Now, what normally happens is, let's say we have something writing to the database. Let me add something let's make it look like it might look in real life. We may have a web server over here, which is what the user gets to. Behind the web server, we may have an app server running the business logic, and then we may have a database. So let's say my cat Cindy was trying to go out and buy tuna because my cat loves to go to the internet and buy tuna. Well, she would go to the tuna-based website, and then at some point she would log into that website and she would purchase her tuna, and then the transaction would be stored in the database. So the database is taking these transactions and writing it to the database. So I hope that kind of makes sense. This is going to be the flow of the user. But back over here, we may have some people in the sales team. And the people in the sales team are trying to determine what has to sell. So they're going to be making a request to the database for information. And that request, realistically speaking, is going to be called a query. And what the database will do is it will respond to that query. So here's the thing to remember with regards to anything. The database has to do work to store it. And it also has to do work to answer questions about the information that's stored in it. Now, at some point, no matter what we do, depending upon the database, we may only be able to write to one node, like in a MySQL database. And if we can only write to one node, not only are we writing to this thing, but all this reading and querying stuff is going to the same node. And that can be very expensive from a computational perspective and use up all the resources. It's kind of like, you may be able to bench press 500 pounds. But if while you were bench pressing 500 pounds, your legs were trying to push on 1,000 or 1,500 pound leg press, at the time you're trying to bench press 500 pounds, you could see that's going to get pretty darn hard because you're being pushed and pulled in all these different directions, and that's not going to work so well. So what can we do? We'll talk later about read replicas, and I may actually introduce the concept now because we'll talk about it more later, but let's actually just talk about what a read replica would be. So, and the read replicas are only with relational databases, but I'll call it a read replica. So in order to make databases scale, one of the things we can do is we can have the database handle all the writes, as you can see, going from the web server to the database. And then we can point these queries to, say, a read replica. So the queries aren't going to this main database over here. They're going to this read replica. And that way you can do your no big deal 500-pound bench presses, and then at a separate time, your 1,000-pound leg presses. That's a whole lot easier than trying to do a 500-pound bench press as a power lifter and a 1,500-pound or 1,000-pound leg press at the same time. So that's going to work. But we're going to remove the read replicas out of the equation, and we'll talk more about, we'll put all the pieces together. And read replicas are only related to relational databases. But what if we could put another server over here and we'll call it a cache? And now what we can do is this. So let's say we've got a couple of people in the sales team and they're all trying to prepare their quarterly reports and they're all looking at the same thing. So we've got little Cindy who is ordering her tuna, and that transaction is being logged in the database. And then we've got this first salesperson, and the first person runs a request. What are the quarterly sales? And it sends it to the cache. The cache does not have access to the information because nobody's ever asked for it that day. The cache then sends it to the database, quarterly sales numbers. The database responds, and now it is in the cache. Now we have the next salesperson that's running their quarterly reports. They run the quarterly revenue reports or quarterly sales reports. The information is stored in the cache, so the cache actually responds. So if we have information that is the same information that's going to be asked in the cache, and a lot of times in a lot of businesses we do, if the cache can store it and keep it in memory, then it's going to relieve this database server over here. So that database that can do less reading and less answering of requests to read, and it can be focused on writing. And whether we're using no SQL databases or relational databases, we can kind of always use these kind of caching things. So I kind of hope that makes sense. Now, I want you to understand this. If salesperson 1 requests one set of data and salesperson 2 requests different data, what's going to happen is salesperson 1 will hit the cache. It won't be there. That's called the cache miss. It'll hit the database, and the database will respond. It will store that information in the cache. Now, if salesperson 2 requests different information than salesperson 1, it's going to go to the cache. The cache won't have it. It'll be what's called the cache miss. It'll go back to the database. The database will respond. The database will put the information in the cache and then send it back. But what if salesperson number 3 wants different information too? Now the salesperson number 3 is going to go make that request, and they'll request the database. They'll do a run a query. They'll hit the cache. The cache won't have it, so it's called the cache miss, and it'll go back to the database, and the database will answer. It'll go to the cache, and then it'll get sent back to salesperson 3. Now, when all these salespeople all requested different information, guess what? The cache was of no help whatsoever. And guess what? If all these people requested different information because that's your utilization patterns, this cache is an extra hop along the way before the database. So if people are requesting different information each time, the cache actually makes it worse. So caching is only valuable if the information requested is frequently requested information. Otherwise, what we're talking here is additional burden on the system, additional latency. And we'll talk about when to use read replicas, when to use caches. And sometimes you need to use caches, read replicas, and queues all at the same time. It's not an either or, but the key here is you must know what your traffic's going to look like ahead of time. If you don't know, what you will do will cause problems. You will add latency, you will break the systems, and you will increase the expense. And that's why for architects like me, when we go into our clients to try to learn about their business and their goals, we're going to create an architecture team of 15 to 50 people, and we're going to be asking questions for 6 months to a year, long before we can think about creating the design. It's not like you're there, you're going to have an answer in 5 minutes. That's not what reality is in real world architecture or real world enterprise environments. So how did that cache help? No. And the chat box is now working, which I'm so happy about. So now that the chat box is working, give me a hashtag AZ305. So the caching helped by offloading requests from the database server or the read replicas, which means it may reduce the amount of CPU, memory, and disk I/O needs we on the database. So why is that so good? Well, it means smaller servers, potentially, for normal businesses. And if we're dealing with a big global business or a giant business, guess what that means? It means we may be able to get them to scale to the kind of users they're going to have at this point. Again, it's going to be something good. So caching can be helpful, but only if the information is commonly requested information. Otherwise, it's going to cause a problem. So let's talk about the kind of caches. Generally speaking, there's several type caches you can use. The more common enterprise fully functional caches that we typically use is what's called a Redis cache. And you can build your own Redis cache on a virtual machine and not use any of the managed features. You can put a Redis cache in your data center. You can have a Redis cache in AWS, Azure, Google. It's a non-proprietary cache we can use. Well, I mean, it may be made by one company, but it's something we can use in all clouds. So Redis is an in-memory data store. What does that mean? It means the cache is kind of like a database. It is a database, if you will. It will process large volumes of application requests, and it will be able to store this information. And it's optimized for, say, distributed data, content caches, session stores, or even message brokers. And we'll talk about messaging in between systems at some point throughout this program. The cache can add a little bit of scalability by enabling servers to do more work. And they work by keeping frequently accessed data in the server's memory. It's DRAM, something that can be accessed much faster than, say, its hard drive, especially with block storage being so slow. Now, the Microsoft cache supports us, Redis 4.0 and 6.0. So with Redis cache on Azure, we can use it as a data cache, like our databases. We can use it as a content cache. We can store where sessions are, like where you're at inside of a session. We can use it for job and message queuing and lots of distributed transactions. So you might see it look something like this. We've got an Azure Web Apps for the front end. We've got an SQL database. Maybe we're caching some of this information coming out of the database or databases that we have. We'd use more than one cache. And you can see it's not uncommon to have Postgres, which is typically a data warehouse, a SQL database to store transactions, and a non-relational NoSQL database to store other things or unstructured data or large volumes of things. And when we talk about data lakes, we'll talk about why we may use different kinds of databases for the enterprise. So that's caching, and we'll get to read replicas and queuing in a little bit. So I want to briefly discuss this concept of a database migration service, and all cloud providers have it. And here's what it really is. If you've got your information in one database and you want to move it to the cloud and you keep it in the same database, especially in the same virtual machine, there's nothing for you to do. If you were on the Oracle database and you move your data from the Oracle database back to the other Oracle database, there's nothing for you to do. But if, and I don't recommend this, but if you wanted to go out of, say, your Oracle database and then go to a Microsoft proprietary database, well, now you can use a database migration service to get you from one database to another. And you could use it to go from MySQL to, say, Postgres, what have you, if there's an appropriate time to do so. It is an automated service, these database migration service. Now, when you deal with the cloud providers, they've got lots of support. You can go from SQL Server to Azure SQL, but you can't run Azure SQL on 3 different clouds, which you might need to do, but you can things like Oracle. So you got to think about whether you should be using a cloud proprietary database in a multi-cloud environment, which is 98% of enterprises. You shouldn't, because it's going to add a lot of complexity, which you don't need if you can run the same databases in all clouds. But if you were going to want to migrate off of a industry-grade, enterprise-grade database to one of the cloud providers' databases, and the cloud providers' databases are great, but you don't want to be going from cloud provider to cloud provider all using different systems. It's like me speaking to somebody in Greek and them translating that into Spanish and somebody translating that into Farsi. By the time and then somebody else translating that into Italian. By the time you're done translating information, it's a lot of integration and things got lost. So keep that in the back of your mind. Industry standard enterprise databases work in all clouds. Cloud provider, proprietary ones are there. But nonetheless, there's still a service to help you go from your current database to your future one, and that's called the database migration service. Migrate MySQL to an Azure database, migrate Postgres SQL to an Azure database, that kind of thing. And the key with these tools is they're automated tools, which means you're going to get some things that are not perfect, but it's going to assist the user in doing it, meaning you don't need to know as much to do it because it's going to make it easier for you. It helps automate and simplify the time with migrations, getting it close to zero downtime, because you're basically taking something out of one and putting it into another, and you're using a tool to do it. These database migration services have very good performance. They're typically fairly efficient with regards to data transfer. They tend to scale to very large databases. They can use secure communications to transfer the data appropriately, and they can help you stay in compliance with whatever industry regulations you need to have. So we briefly talked about it. So next we're going to talk about data warehousing databases. Postgres is a data warehousing database in most cases. So what do data warehouses do? Well, realistically speaking, they are databases that store vast amounts of data. And we'll talk about data lakes and we'll talk about how all these big pieces of the big data parts mine together soon. But understand that a data warehouse is designed to store a lot of stuff. And the reason businesses create these data warehouses is that we throw all this information into this database and we've got it nicely sorted and easy to find. We can now perform an analysis. For example, let's say you are in the airline business and you've got historical data based upon what happens geopolitically and how that could affect the price of oil per barrel. And if you're going to purchase your next 3 years or purchase an option contract on your next 3 years of fuel, like an airline might do, we may be able to look through this data and be able to figure information out. We may also find out that there's a month of the year where that business does a lot of business, and maybe there's something they do that month that they could repeat throughout the year. But the point is, to running these databases is just get information and then be able to analyze that information to make better business decisions. And that's why when you deal with a big data warehouse, they're typically involved in sorting data, and we typically use tools to be able to look at the data and see if we can look at it and see something and it's going to graphically represent it to us. And there's typically a tool for prepping and loading the data. Typically speaking, like an extract, translate, load tool, or an extract, load, and extraction, transformation, loading, or the other way, ETL versus ELT, based upon what you want to do and why you want to do it. So what we're typically doing and what this kind of stuff all looks together is, let's say you got some data. You may actually pop it in, ingest it initially into your object storage. You may use Azure Synapse or some form of analytic storage. That may go into your data warehouse, whatever. Sorry, say you're going to store it somewhere, and then you're going to analyze that data from your data warehouse, and then you're going to visualize it in a tool like Power BI. So that's kind of what we're typically talking about in data warehousing. Before I get to data lakes, I'm going to take a few minutes to see if anybody has questions on what we've done thus far, and then we'll get back to the content. So, Chris, were there any questions? If there are none so far, I'll wait about 30 seconds. And if not, I'll get back to the content, because I think I was having fun going through this content. I hope you guys were as well. Give you guys just a few seconds. Well, now we will have some more fun. Can you use read replicas instead of a cache? Well, you might need to use both. So read replicas are used to maximize the read load. Caching is used to offload the read replicas or the database. So Faisal, let's say we have a NoSQL database like MongoDB. We can't use read replicas with MongoDB or Apache Cassandra. So keep that in the back of your mind. But I'd like you to think about why we're getting into all this caching and queuing. The reason we're getting into the caching and the queuing is as follows. We have to expand. And you're going to reach a point where you can have database servers that have 256 physical cores and 8 terabytes of DRAM, and they're so out of capacity. And we might need 16 read replicas with that, where we have 4 read replicas and they're all stacked. And then we still need caching. So you have to put it all into context. Most architectures that I work on are at least $1 billion projects, at least minimum. Otherwise, I don't really work on them. They go to more junior level people. But if you think about it, if you're putting $1 billion into technology that year and another $1 billion into technology that year, you have to understand the demand for your tech is huge. Amazon does roughly $1 million of sales a minute. $1 million a minute. Or is it $1 million a second? It's something crazy like that. And imagine how many hits are going to go to them. And when you're at that scale, you're going to need, for relational databases, is use read replicas and use caching. And you're also going to need to use queuing. So it's part of the whole strategy. It's never a place where we just got one tool. It's about using all the tools that you have. Great question there, Faisal. What happens when the cached information changes? That's a great question. So when cached information changes, the cache is going to need to be updated or invalidated to reflect the new data. Because if you're pushing old data, well, that's not going to really hurt you. Now, it can be done a lot of ways. You can manually clear a cache if you wanted to, like you made big changes. You can set up a cache TTL or an expiration time that says after 3 hours, it should change. And that way, you can determine what it is on a programmatic basis. Or you can have it triggered by the actual system itself, depending upon your cache strategy, like a write-through cache or a cache invalidation. Does a cache store queries? Not exactly. It's not that the cache stores queries, it stores the data from the query. So let's say I wanted to see a photo of Cindy the cat, and somebody else requested Cindy the cat. The cat is going to store that same photo of Cindy the cat. It's not going to store that Mike asked Cindy the cat. It's going to store the information for the Cindy.cat.jpg. Still curious how these Azure database services compare to Fabric, which is MS is heavily promoting. So Azure databases focus on database management, whereas Fabric is more like integrating multiple services like Power BI, Data Factory, and Synapse for unified analytics. Fabric is more of a comprehensive analytics and data orchestration strategy. So when it comes to big data, we're going to have all these different databases. I mean, you're not going to find an enterprise that doesn't have, relational databases, no SQL databases, data warehouses. They're also going to have all this information in object storage, information in file storage. And somewhere along the line, and we'll talk more about this when we get to data lakes and other things, you've got to take the data, you got to normalize the data. So imagine if in one database, Mike Gibbs is spelled MikeGibbs in all caps. And in another database, it's spelled lowercase. And in another one, it's capital M for Mike, and then IKE is lowercase, and G is capitalized, and IBBS is lowercase. We've got to normalize that data because on the surface, it looks like very different data. So we'll have to do these things. But Fabric's more about the whole putting all the pieces together. Now, thinking about it, do you want to use a proprietary thing like Fabric? Well, if you're one of those companies that is only in a single cloud, which is 2% of the enterprises, then yes. But otherwise not. So why would a cloud provider push these services? Well, if you use too many proprietary services, it becomes near impossible to go somewhere else. Amazon ECS for container orchestration, you're stuck. Whereas if you used an OpenShift Kubernetes across 3 clouds, you're not stuck. So I kind of hope that makes sense to you. So, the Fabric is great. But the question is, should be using that, or should you be using a tool that works in all environments? And I'm not sure if Fabric does or doesn't. What is the underlying infrastructure under an in-memory cache? DRAM, random access memory, which is the fastest memory. So yesterday, if you were here, I opened up a server and I showed you DRAM sticks. That is the fastest. So when it comes to memory, a magnetic hard drive is slow. A standard SSD is relatively slow. An NVMe drive is relatively fast. We can create a RAID array, like 10 NVMe drives in RAID 0, and that almost gets to the speed of DRAM. but DRAM is faster. So we're going to be using the DRAM. And for the last question, caching in a database is very similar to the caching in a content delivery network. None of this stuff is new. Caching is old technology. Queuing is old technology. Virtual machines are old technology. All the stuff that sounds new and exciting is 25 to 50 years old. The names have changed and maybe the speed has changed along the way, but it's all old technology. So if you ever want to see anything, if you ever want to go to the Internet Engineering Task Force, IETF.org, you can see all the network specifications, all your Cisco certified internet experts or Cisco certified design experts, and anybody who's anybody in networking gets their information there. You can see there's an RFC called 1925, and then it says all technology will be new again. And basically you smack a new name on it and you use it in a 2% different way than it used to be, and it's new tech. So kind of hope that makes sense. But very astute. Doing great to see that this is a similar concept. That's what I need you to get to. And when you figure that out and you realize that there's only a couple things then to call technology and it's all just repurposing of everything else, you'll know every cloud, everywhere, every time, and every new feature that comes out, you'll be seen it, been there, done it. Now I know what it is. That's how you stay current in technology, but rock solid fundamentals. All right, so we're going to get back to the content. So give me a hashtag AZ-305. And again, tomorrow, why don't you join us on the How to Get Your First Cloud Job webinar? It's completely free. It's on Zoom. We'll be talking about cloud architect careers and solutions architect careers, but you want to learn about enterprise architect careers, AI architect careers, security architect careers. I don't care. We'll do anything we can to help you in this free webinar. So now let's talk about data lakes. Love data lakes. I love having access to information and doing stuff with it. So let's talk about a data lake. A data lake is going to be a technology that's going to let you store and work with a whole lot of data. And we can use this big data for analytics. We can use it for machine learning. We can use it for any AI approach we want. And data management systems, the whole point of all this stuff is to be able to look at the information we have and figure it out. Imagine looking at handwritten ledgers the way it used to be, where people would just write information on paper and then figure out how to actually figure out what the heck was going on with all these paper records. Well, at least it takes huge teams of people to do it. Now we can have one or two people that can leverage technology to do it for us. So when it comes to data lakes, we are going to be dealing with lots of different data sources. And we typically need the following: a database or databases that store the data, tools to look at the data, and tools to prep and load the data. So a data lake is going to be a repository of data stored in natural or raw format. It could be PDF files. It could be objects and object storage. And the point here is we're going to take structured data, like database type stuff, and unstructured data, like photos of my cat Cindy, for example, and we're going to put it in, or PDFs, we're going to put it in one place. Now we're going to store this data at huge scale. I mean, we could be talking about petabytes of data. So the data lake is going to be the location that holds this data. And why? Now we've got the data in the data lake, right? What can we do about it? We can run machine learning on it. We can do lots of different things. So data lakes are a really important part of big data. And the way it's typically done, we can draw one of these out so you can see what a data lake is typically created by. I'm not a big data architect. If you're more interested in data lakes, there's a video on our YouTube channel where I interviewed Praveen. Praveen is someone we trained to become a cloud architect, and he got a great cloud architect job at JP Morgan Chase Bank. But prior to us getting him that job, he was working as a big data architect, and he is an expert of all experts of big data and data lakes. And he did a nice live stream video on our YouTube channel explaining it to people. So my team will find that and place it for you. But imagine a world you've got a relational database. Let's say Oracle DB, that's your relational database. Now let's say we have MongoDB as our NoSQL database. You can be anybody you want. MongoDB could be AWS DynamoDB, Microsoft Cosmos, Google Cloud Bigtable, but we're going to use ones that are typically used in the real world that we can use across all clouds, because we teach multi-cloud architecture and 90% of the businesses use multi-cloud. So this would be our relational database, and I'll call it RDB. This would be a NoSQL database. And now let's get a data warehouse here while we're at it. Let's call this Postgres. So now there's our 3 databases. Now we may also have this object storage. And I call object storage. You're not going to hear me calling it blob. And here's the reason why. If I'm working as an architect, if I walk into my client's office and I can tell to their C-suite, like their CIO and CTO, and if I walk in there and I have some exciting blob or S3 or whatever, they're going to laugh me out of the room. Now, if I talk to them about object storage or block storage or file storage, they're going to know what that is. We're going to be speaking in the same language. I'm not going to be using any jargon, and they're going to take me seriously. So I'm always going to use generic terms, and that way you'll understand what it is. If you're on Google, Azure, AWS, Oracle, who cares? It's the same stuff. Kind of like where your eggs, we buy your eggs. Does it matter which supermarket it is? All these clouds provide, for the most part, the same thing. So typically what you need to do is you'll take these things, and somebody will write these PySpark scripts and big data frameworks. And what they'll do is they'll use this to normalize the data. And it's called mapping and reduction, the process of taking the data and normalizing and mapping it so it can be used later. And that's why there's tools like Elastic MapReduce on AWS, and Azure's got their tools too. But just to understand, PySpark is going to work in all clouds, so you don't have to worry about any of these things. So typically speaking, we'll have these sort of things. Now, what'll happen is after all this stuff is here, there'll be some form of a landing zone, which is where we're going to send all the data. This is going to be the clean, the normalized data. And this data is going to come into that, big data environment. It could be considered a landing zone at that point, a data lake, what have you. And that's the basis of the way these things are found. But now we've got this data in the data lake, if you will, and now we can catalog the data so you can find it. And we can do a few other things, but now look at this. We know what the data is. All the data is normalized. We can go here and we can send this clean, good data to some form of machine learning engine. And whether we're trying to create generative AI out of our data or we're trying to analyze statistics out of our data, that's the reason organizations kind of do this. And that's traditionally what a data lake is. We're pulling all this data, we're storing it in this environment, it's been clean data, we kind of catalog the data to know what's there, and then we can do whatever we want the data, or not even get this involved and figure it out later. But data is very helpful when you're making decisions. I'll briefly discuss data share, and that's going to be a publisher subscriber-based data sharing tool. It gives you the ability to create a snapshot based and share it for sharing your data. It enables you to take data that you have and maybe share it with multiple customers or multiple partners. And that way it's fairly easy to manage and monitor the data that's shared, because you may want to share data. Maybe you're a business that sells access to your data, but you need to know who shared it and what's been shared and by whom. And that gives you the ability to create an audit log, etc., what have you after the fact. So as we talk about databases, we should talk about some Azure database optimizations. And this is about right-sizing your database. So if you use a server that's too big, move it to a smaller server, and it's going to cost less. Maybe the database is no longer useful for you, and you should terminate it. Maybe you need to update the database. So that's what's really considered right-sizing, to optimizing your databases in there. Maybe we've got a database and we want to encrypt the data at rest and in transit. Maybe we need to go through a firewall for the database and we need to open up ports on the firewall. Maybe something's misconfigured. So that's really what we're talking about. Now, we might want to run some scripts to snapshot our database. So maybe we want to configure a backup, start it, script it, snapshot our database, do a little work when we're done, and then do an incremental backup. And we have that ability with the Azure Backup Service to create these beautiful backups for us. And the Azure Backup Service is going to provide a very simple, secure, and very cost-effective way to back up data and recover it from your SQL servers and Azure virtual machines, SAP HANA databases and virtual machines, database for Postgres servers, what have you. And really, you're basically going to specify which server that you want to protect or back up, and Azure Backup will install a service. And basically, it's an extension that includes a coordinator and an SQL plugin. Now, the coordinator is going to be responsible for triggering workflows for various operations that are going to have to occur. And the plugin is going to be responsible for the actual data flow. And we'll be able to discover databases on the virtual machines, and Azure Backup will create an account for the backup and restoration of these databases. Let's briefly talk about transparent data encryption. So transparent, and I introduced it a little yesterday, but I wanted to go a little more here. So transparent data encryption is going to protect your databases like Azure SQL, Azure SQL Managed Instance, Azure Synapse Analytics Service, and it's going to protect it against the threat of malicious activity because it's going to encrypt your data that's actually at rest. And transparent data encryption is enabled for all newly deployed databases or Azure SQL databases. You can manually enable it for older Azure SQL databases. Transparent data encryption is going to occur with the key vault. We'll set up a configuration of data encryption, and that will encrypt and decrypt the data on demand. So when you write the data to the database and it's stored, it's encrypted. And when you pull it, it's decrypted. And we can use a key vault, which is a hardware device for the storage and management of the encryption keys. Because if you encrypt everything and then you lose your decryption and you don't have your keys, well, you won't be able to make any heads or tails about it. That's the whole reason you're using encryption in the first place. So another part now that we're going to talk about scalability, and this only pertains to relational databases, are read replicas. So we're going to have two kinds of scaling: vertical scaling, horizontal scaling. Vertical scaling is what most of you do with your computer. I ran a Mac Pro with 16 cores. It wasn't strong enough to handle my workload. So I built a Threadripper system that had 64 cores and a half a terabyte of DRAM. I had no problems with my workstation. It ran great. So vertical scaling, bigger server. But here's the thing. No matter what, you're going to reach a point where no matter how big your servers are, they're just not going to be enough, and you're going to need more of them. So horizontal scaling is adding more. Vertical scaling is like putting a 300-pound football player that's all muscle in a boat and asking him to row or her to row. Horizontal scaling is like putting 20 people on a crew team that are all rowers that are all going to row at the same time. They're not as big, they're not as strong, but you got 20 versus 1. So scaling up is the simplest, but at some point it's just not going to work. And think about it this way: you only have one server and the server dies. Not necessarily the optimal thing. With the read replica, we can turn that into a primary database because it's got a read-only copy of the database if we need to. So now we're getting the concept of read replicas. A read replica is an actual replica of the database. Full read-only copy. So what happens? You're going to write to one database. I'll map it out for you, and you'll read and you'll direct your reads to the read replicas. Now, it's an asynchronous thing. You write to me, and I push it to the rest of them. So kind of think of it that way. Here's what it's going to look like, and I'll show you in a minute how we'll put these pieces together after we do the queuing piece. So here you can see we've got a primary SQL database. This is the master node. Now, if we do nothing, all the writes are going to be directed to this and all the reads. Well, that's not going to scale. So now what we might do is put some read replicas here, and we can layer these read replicas deep as well. So we may actually pop a read replica to this SQL database, another one, and another one. So now what we do is we direct all the users and all the read traffic to these read replicas. And guess what? The only thing this database does is write, read. So you can see how that's going to help offload it. Offload the read traffic. Bear with me. So that's realistically what we're talking about. So before we put all the pieces and parts together, and read replicas, I'm going to say this, are only for relational databases. I'm going to say this again. Read replicas are only for relational databases. There's no concept of it in an SQL database. Now, there are SQL databases like MongoDB where I can read and write to all nodes. I'm sorry, the Apache Cassandra that I can read and write to all nodes. So that's going to scale much easier. So now, we talked about read replicas. We talked about caches. We're going to talk about queuing briefly. And then after we talk about queuing, then we're going to put the pieces and parts together for you from more of an architectural perspective. A queue is a place to store a message until it's delivered. When I first learned about queuing, and it was related to queues on a wide area network and how you scheduled your sending your data on the WAN, it didn't make any sense to me. And then I went to England and I realized that a queue was a line. When you get on an airplane, they say form a queue. People that need help first, then disabled people first, then first class people, then the back of the plane this, and that way they got everybody on the plane in an organized manner. If you're like me and you went to the old Greek airport like 30 years ago, and you're in that airport and they're like board the plane and everybody's trying to get on the plane, well, that clearly didn't work. Form a queue. Okay, you go first, you go second, I go third. So queuing is a way to store messages and schedule them on their way to the database. I want you to think about this. You're trying to send a message to the database and the database is busy. You lost the message. What if the database order is $40 million of routers and switches and it doesn't hit the database because it's busy? Well, then you're going to have an unhappy manager that your $40 million sale of routers and switches, let's say you work for a networking company, didn't go through. So the queue is a place to store a message and not lose it until you're ready to use it. So message will be put in the queue and it'll be removed from the queue. Now, Azure is going to have two types of queues. It's going to have storage queues and storage bus queues. Now, a storage queue is a service that's going to store a large number of messages, upwards of millions. And these messages can be accessed globally through authentication calls, either via HTTP or HTTPS. Each message in the queue can be 64 kilobytes in size, which is quite big for an actual text that we would typically use. And it's going to provide a fairly well and uniform, consistent programming model across all queues, tables, and blobs. And it's optimized to create a backlog of work waiting to go to the server when the server is ready. Now, with the storage queue, there's no guarantee in the order and the way they actually leave. There is also the service bus queue if you need to guarantee the order. And that means you can send the first message that goes into the queue, the first one out. Next message in, next one out. Third one in, third one out. Sometimes you need to order these messages. And sometimes you just need performance and you want to get it through as fast. So your architectural decisions, which are based upon your business needs, and then hence your technical requirements, will be based on determine these things. So service bus queues are for FIFO. So now let's kind of put the pieces and parts together. Let's kind of look at the caching, the queuing, and where we might use some of these things. So let's say I have a relational database here. Let's pop my database over here. First thing we need to do is we need to get my absolute favorite user. And let me get my favorite user who's going to be using the system. She's my absolute favorite computer user. I personally think she's terrific. I went to adopt her to make my wife happy, and the next thing I realized, I've got this little loving thing that follows me from room to room. It's pretty great. So now she wants to go to her web server because she's in the process of ordering tuna. So we've got a website. Then we've got an app server. And then we have, on the way to the database, we've got this queue thing. So we can explain this. Then we'll add the other elements. Make it a little bigger. Yeah, trying to learn how to spell queue can be another one of those things. So here's that. So now, and then behind this, we're going to actually have the database. So now what's going to happen is, let's say Cindy wants to go buy tuna from whatever website she found her tuna. She goes to the website, she's surfing around, and she does this by walking on my keyboard with her cute little paws. She's got very cute paws. And then she hits the website. Then Cindy logs in with a username and password. Username Cindy, password Cindy. Obviously nobody would use that, but a cat might. Now, her order gets put into this queue over here. And Cindy likes this cat treats called Bonkers Purr Pops. The other day, I had literally ordered her 100 bags of it. I'm not joking. She loves them. But let's say she got a hold of my credit card and she ordered 1,000 bags. So there's an order of 1,000 bags of these tuna, freeze-dried tuna treats that she actually likes. And the database is busy right now, so the message is in the queue. And as soon as the database has information on it, the transaction is recorded in the database. Then the order is created. And happy little Cindy is going to get her cat treats, her tuna lollipops, and she's actually thrilled. Now, let's kind of, so you can see how the queuing will do it. Now, imagine if we were trying to throw 1,000,001 messages in a second at this database. What's going to happen is the database will run out of CPU resources. The CPU will hit a high level. And then after it hits that level, poof, it's just going to drop messages. So now we can, and what is it typically going to look like if you actually look at utilization of your CPU? You're going to see spikes where it's too busy. Then you'll see it go down. Then you'll see a spike to nearly 100%. Then it'll go down to here to nothing. Then you'll see another spike. And normally speaking, when you're here, you have performance problems. With the queue, we're going to, I don't know what I did there. With the queue, what we're going to do is we're going to come in and out at this nice average threshold, avoiding the peaks and valleys. We're going to be only giving the server what it wants. So that's where the queue is going to help. Now, I want you to think about a few other things we could do. So now we've used the queues, which helped reduce the write load, because the queues are used as it's running into the system. What about read load? Well, behind here's going to be your corporate users. And the next thing we're going to do is we're going to put a read replica, or maybe a couple of read replicas. So RR, read replicas. And now we've got the corporate users. Let's say we've got 50 or 50,000 corporate users, which is not a lot. Amazon has 1.5 million employees, to put it in the context. Microsoft has 250,000. Some incredible earnings with that 250,000, but that's neither here nor there. So now when the people in the company need to request information, they go to the read replicas. Here we go. Cindy wants to order something, or another cat wants to order something. They hit the same web servers, app servers, get put in the queue into the database. And here's your corporate users trying to figure out how many cats ordered cat lollipops that day. They're constantly checking. They want to see how big their bonuses are going to be. They're all kinds of excited. Now you've got so many corporate users that are trying to figure out how much tuna lollipops and how much pet food's been sold from this miraculous pet store, that these read replicas are overwhelmed. So then we need to look at our information and say, well, if all the information is different, well, then just add a lot more read replicas if it's different every time. And what's each read replica? Another server, which costs a lot of money, especially in the cloud. They cost much more than they would in the data center. So we've got a whole bunch of read replicas. And now all of a sudden, even though we've got a whole bunch of read replicas, we still don't have enough for the people at the company that are trying to figure out what their sales bonus is going to be on the pet food. So now we stick a cache over here. And then the cache is here. The corporate users hit the cache. If the information is there, they get their information. If the information is not in the cache, it's a cache miss. One of these read replicas responds, and then the cache will have that information. So if your information being requested is constantly going to hit the cache and be in the cache, maybe we can get rid of a lot of these servers and save some money along the way. If the information is constantly requested is different, then maybe we need more read replicas. So generally speaking, scaling databases is going to, after we know what our traffic is going to be for relational databases, read replicas and caching to reduce the read work. Read work is caching and queuing, and write work or sending to the database read work is done by read replicas and caching, and write load is reduced by queuing, giving us a place to store the messages until we don't need them. I hope that actually makes sense. That's how we're scaling relational databases. I'm briefly going to touch on Azure Data Factory, and that's going to be a technology that orchestrates and operates the processes to refine enormous amounts of raw data into actionable business insights. It's a series of interconnected systems that provide an end-to-end platform, and it's optimized to scale out for serverless data integration and data transformation. I'm going to touch a tiny bit about designing your databases for high availability. Then we'll take some questions, and then we're going to get to the real fun stuff, networking, or at least fun stuff for network architects like me. So the next thing we're going to talk about is, Azure's high availability database. You want a really high availability database? Use something that can write to multiple nodes and stick it in 3 clouds. That's how you make a high availability database. But when it comes to these exams, and even if we're in a single cloud, we still have to create a higher availability system. So the first thing we need to do is make sure that our systems are available when we need them. And Azure kind of has these availability models. They call them standard availability model and premium availability model. So in the standard availability model, it basically separates your compute and storage, and it relies on the high availability and reliability of your storage to our being remote, because they're not inside the virtual machine. And this is a budget-conscious way to make your systems work. And it can tolerate, performance degradation during maintenance. Now, the storage is there, but it's not exactly super high availability. It's designed to be low cost. The premium availability model with regards to Azure's designs for high availability is based on a cluster of database engines. And this is designed for mission critical applications, meaning stuff that has to work with high input and output, read writes, that kind of thing. And it relies on a certain number of database nodes. And by doing so, we can guarantee a high transactional rate and lower latency. So what we're dealing with is zone redundancy. Basically, it's going to put your database in multiple data centers, and Azure Traffic Manager will direct it. Primary database with these secondary read replicas in other data centers, and you can use them as a primary database should things go wrong. But you got to remember, it's in the same cloud. You have a major problem in the cloud, you are going to lose everything. So kind of think about that. You might look at it this way as and these beautiful pictures, you can thank Alonzo from my team. He can really draw some great graphics. You've got Azure Traffic Manager that's pretty much sharing loads between multiple data centers, AZ data center, same thing. And you can see that you've got your primary database and you've got backups across these data centers and what's called an always-on availability group. So you've got the systems that will work. Right. I think it's time for us to take questions. So let's do that for a few minutes. Oops. You're not there with me. What is what is the caching in Cosmo DB called? For example, DynamoDB has DAX and AWS. Well, here's the thing. There is an Azure DB proprietary type cache that you could use. There absolutely would be. And that's the Azure DB integrated cache, which stores frequently accessed databases in memory. And it's similar to the AWS DynamoDB DAX. But should you be using DynamoDB for an enterprise? Should you be using Azure Cosmos for an enterprise? 98% of companies use more than one cloud. So the second you use Cosmo DB or Google Cloud Big Table or Microsoft DynamoDB, you're locking yourself into a single cloud, into a single proprietary solution, and you're going to make your architecture less flexible. And the whole point of cloud computing is flexibility and agility, meaning do what you need quicker. And as soon as you introduce these concepts of proprietary anything, understand it's going to make it much harder to support your client and their future goals. Stick with things that work everywhere. Life's easy. Stick with things that are more proprietary. It's more challenging. So just keep that in the back of your mind. What is normalization in the data lake here? Is it similar to database normalization? So normalization, or that mapping and reduction that we're talking about, refers to organizing and structured data. We're trying to reduce redundancy, and it's fairly similar to database normalization. But we have to remember, in the data lake, we don't have to adhere to these strict table designs. So normalization is really more about efficient storage, better query performance, and making sure that our data is consistent and clean. It's got a data hygiene element of it. Great question there. Is TD encryption at rest or in transit? It's actually at rest. So when the data is stored, it's encrypted. And when the data is pulled, it's decrypted. Now, if we use that with, say, SSL/TLS-based security, we can make sure we can encrypt and decrypt in process. But the transparent data encryption is transparent to the user, meaning it's as it's stored. I may have miscommunicated that yesterday. What happens to the cache if the power goes back on and off? So here's the thing. In a real data center, you won't have the power going off and on. In a real data center, they will. And in fact, the only time I've ever heard of a data center having a power outage was AWS when they had an outage several years ago. Now, did they have a power outage? Was it something else? I have absolutely no idea. But data centers don't have power outages because they typically have multiple power companies coming in, different power transformers, generators, backup generators, and batteries. So you should not have a power failure in a data center. And if you do, the people that designed the data center probably didn't know what they were doing. But if the power goes off, things that are persisting in disk storage will stay there, but messages that are in DRAM will be lost. So we have to understand the way it's configured with persistence or replication. We can configure these things to save data periodically, but if we don't, it will be lost. But you should not have a power failure in a well-architected data center. Now, there isn't a read replica in a non-relational database. Absolutely. How do you reduce writes for dynamic data? That's the purpose of using the queuing. We also have to remember that non-relational databases tend to scale better. And let's say we use Apache Cassandra, because when it comes to a world where 98% of organizations are multi-cloud, You almost don't want to touch a DynamoDB or an Azure Cosmos or a Google Cloud Big Table because it's like handcuffing yourself to the desk and saying, I can't do anything. So we have to understand that things like Apache Cassandra can write to all nodes. So we can have 10 different Apache Cassandra servers and we can write to all of them. We don't even have this problem in the first place. And NoSQL databases scale to more writes, be the way they're architected and the fluidity and the eventual consistency versus the immediate consistency. So it's not really so much of an issue with NoSQL databases. Kind of hope that makes sense. But queuing is what we would use. Freedom Lands, from a network point of view, what is queuing and what is caching? So from a network point of view, here's what we're talking about queuing. It's a little bit outside this course, but I'm happy to explain it to you. So let me draw this out for you. So let's say here is, bear with me. So let's say this we have in this particular, what do you call it? So let's say we've got a 10 gigabit link. It could be a cable from switch to switch. It's typically a wide area network, but this is 10 gigabit. And let's say we've got video, uncompressed video that's realistically spending is 5 gigabit / second. And then we have business work. These are gigabytes per second, or these are the same. We're going to sort of Mac. Now we've got business stuff. Now we've got user traffic. And that's going to be 1 gigabyte. Does anybody see a problem here? We've got 5 plus 5 is 10 plus 1 is 11. Now user traffic, user traffic could be something simple. Let's say this is people going to websites traffic. Web traffic is TCP and not UDP. So by doing so, if I send a message on a link that's TCP and it's lost, I just resend the message. But video is generally intolerant, 100% intolerant to delay. So we might actually create a queue on this link, and let's say this is 5 gigs, and we might say, in times of congestion, video gets 5 gigs. And we might then say, if enough traffic is available, give the business 5 gigs. All other traffic send if and when there's availability on the link. This is where the extra traffic would go, if there's availability. So if there's no availability for your traffic, nothing goes except for your video and your business critical traffic. That's why we're typically creating these queues. But I want you to also think about the security implications of why network architects like me typically implement one of these quality of service processes. So let's say we've got a worm, and the worm is generating 50 gigs of traffic, and we only have 10 gigs. Well, if we prioritize the business, which is 5 gigs, and then the video, which is 5, we prioritize the business, which is 5. Now this worm wants to send its worm data, infect our entire systems, and it's got no place to go. It can't fill up our thing. So that's where we're using what's called quality of service. It's often called queuing in networking, and that's the point behind it. Let's see where this. And caching, when it comes to networking, we would use much in the way of a content delivery network. So bear with me. Chris, remember 337. So caching from a where we would use it on the network would be more like this. So caching for, say, a website or a content delivery network. So here we've got the user, Dimitri. Dimitri is over here in Athens, Greece. Dimitri goes to a website. It's not there. It gets sent to the origin, which is, let's say, in Palm Beach, Florida. Palm Beach, Florida actually answers. It stores the information into the point of Greece, and then it sends it back. And then it sends it back to the user. Now, 5 minutes later, we have a lady. Her name is Evangelia. Evangelia wants to go to the website, and it's already sitting in the point of presence, so it gets sent back to her. It says the request goes to the point of presence, and then it gets sent back. And then after Evangelia gets her thing, Maria decides to get her thing. So Maria sends her information. It hits the Azure point of presence. It's already cached there, and it gets sent back. But now, out of nowhere, now we have Onikolaus, and Onikolaus wants to get information, and it's not in the cache, so it goes all the way back to the source, and then it gets sent back. Oops. And then that gets sent back directly to Onikolaus. So I kind of hope that actually kind of put that together. Hope that helps. All right, back to the content. So Tech Travis, myself, and Mark Milovanovic, we're both Cisco certified internet experts and network architects. We put together a subnetting workshop, and we also put together a BGP workshop, and both of those are absolutely critical networking things to talk about. And that's about 12 hours of work that you can get completely free on our YouTube channel. So I hope you actually do that. Bear with me a second. And while we're actually at it, I want to know that you're awake, you're alert, and oriented. So maybe give me a hashtag AZ305. I have to do the YouTube thing. I'm on YouTube today, so I'll pretend to be a YouTuber. If you're enjoying this video and you're learning something, please hit the like button. Please subscribe and hit the bell to be notified of new videos to assist you in your technology career. So that's what we love doing, helping people in their careers. We're all focused about the career. So now let's talk about some basic networking. We're going to start with the OSI model. And this is one of those things that we actually drew some graphical content on. Now, why did we come up with this OSI model? What's the point? Well, you see how the ridiculousness that AWS calls a virtual machine an EC2 instance, and Google calls it a compute instance, and Azure calls it a virtual machine, but it's the same, 1999, 25-year-old base technology. Talk about miscommunication and problems. I mean, that's an absolute nightmare. It's absolutely crazy. So in worlds where we need to have precision communication and not make errors, we use a standard language. If I talk about a beta blocker, which is a type of medication that's used to reduce blood pressure and reduce the workload on the heart, if I mention the word beta blocker in England, in Australia, in Europe, in Asia, the Middle East, everybody knows what a beta blocker is. Why? Because we can't afford to have misnames in medicine and have people die. When you get on an airplane and people use English, they use a phonetic alphabet to communicate. Alpha, Bravo, Charlie, Delta, Echo, Foxtrot, Golf, Hotel, India, etc. And they're doing that because that way there's no miscommunication. In medicine, we use standard abbreviations because who knows what these abbreviations can mean. VM could be voicemail, vulnerability management, virtual machines. So in networking, we don't play games. If the network doesn't work, everything falls apart. So we came up with a common language and a common set of layers to describe networking. And they are layers 1 through 7. Networking, for the most part, is layers 1 through 4. Layers 5 through 7 are your PC people, your developers, and all that other stuff. But we networking people typically work at layers 1 through 4. So now let's go back to this chart and talk about what this is. Layer 1 is the physical layer that we're dealing with. You got a piece of fiber, a laser, fiber optics on each switch, and a laser on each switch. That's layer one. You've got a copper wire that you plug in your computer to the switch. That wire is layer one. Now, on your PC, you plug that wire into your Ethernet port, right? You plug it in, and all of a sudden it connects to the network. The card level is the data link layer. So at the physical layer, we're sending either bits or we're sending photons or light across a wire. At the data link layer, if it's Ethernet, we're sending frames. And for the most part, it's the frame relay. We were sending frames to in other forms. But layer one wire, layer two card. Your Ethernet card is layer two. And you may notice on your Ethernet card, it actually has a hardware address. It's called the MAC address. It is burned into the card. It's there. It is a physical thing. Layer one wire, layer two card. Now, layer three is going to be the network layer. In the old days, we had Apple Talk addresses. Boy, they were fun to work with. We had IPX addresses in the Novell network kind of days. And guess what else we have? Now we're in a world where we have IP addresses, IPv4, IPv6. If you're behind a firewall, chances are you're either on the 10.0.0/8 network, you're on the 172.12.0.0/12 network, or you're on the 192.168.0.0/16 network, somewhere along that. That is your logical IP address. Every device in the entire world needs a different IP address in order to communicate with each other. And if they're overlapping, you're going to have to translate those addresses to make them unique with NAT. So layer one wire, layer two card, layer three address, logical address that you assign to it, either by manually going in there and popping the address in or via the dynamic host configuration protocol. Now, the next layer is the transport layer. And at this layer, we're actually sending something called segments, where at the network layer, we're sending packets. And if you ever hear anybody talk about packet loss on the line, what they're saying is IP data is being lost. But the transport layer is how do we send it? So there's a couple ways we can send it. We can send it via reliable transport. So here's what reliable transport is. If reliable transport, I send something to someone and they confirm that they received it. So if I was sending data to Alonzo, I'd said, Alonzo, here's your data. This is the way TCP works. Alonzo would say, Mike Gibbs, got the data. Send me some more. And I'd send him the data, and Alonzo would say, yep, got it, Mike. Send me some more. And if I sent data to Alonzo and Alonzo didn't respond, I'd know he didn't get it, and I'd resend it. That's reliable transport. So if it matters at this level, I use TCP. But what if it doesn't matter? Or worse, it's real time. So with regards to real-time traffic, we use something called the Uniform Data Protocol, or UDP. And that's data that we send. So I'm trying to send Alonzo as much data as fast as I can. If he doesn't get it, well, he just missed it along the way. Now, why would I use something like that? What if I sent you, what if I were to send you a message and it involved retranslation? So what if I sent you the message via UDP, how do sales reps get appointments? But the word get goes away, and all you got was how do sales reps appointments? Well, that's not perfect, but it's still there. Now, what happens if we use TCP? So what would ultimately happen is, maybe we lost some data along the way and it had to be retranslated. And what if how got there, sales reps got there, and then after the came back because it was retransmitted? Well, that would be an absolute disaster. So we don't want to retransmit certain types of data. And when we're dealing with voice or video, we can't afford to retransmit words, a minute later after the rest of the data was received. That would just be all kinds of wacky. So going back to this, TCP is used for reliable things. You need to send a file that's 10 gigs and you need to guarantee they receive it. You're using TCP. You want to see a streaming video of a cat eating a cat lollipop? Now that's going to be UDP. Now, at the transport level, we also have this concept of ICMP, or Internet Control Message Protocol, which would be used for ping. Like if I want to see if something's out there, I might ping an IP address. For example, I might also do what's called a trace route. So if my data is not making it somewhere, I might do a trace route to see which router hop the data stopped on. And that's all the Internet Control Messaging Protocol. So going back to this, layer 1 wire, layer 2 card like Ethernet card, layer 3 IP address, layer 4 transport TCP UDP. Layer 5 is the session. And at this point, we're sending data. And this stuff is more outside of networking, but understand it. Layer 6 of the presentation data is really about presenting data to the upper levels, to the applications that you use. Now, one thing that networking people actually think about at the presentation layer is encryption. So this is where like your TLS encryption actually lives. So even though we networking people say we're layers 1 through 4, we kind of get involved into this layer 6 stuff, this encryption stuff along the way for our data. And then the application layer is what you use. So I go to Mozilla Firefox. My wife thinks it looks like a cat. She calls it the cat. I call it the cat too, but even it's a fox. When I open that Mozilla Firefox, that's an application that I actually use. That is layer 7. So layer 1 wire, we send bits. Layer 2 data link or card, we send frames. Layer 3, we send IP packets, and that's the IP address or the logical address. Layer 4, TCP, UDP, ICMP. Layer 5, it's the socket, which is really a combination of protocol. It's like the IP address and the port number. Layer 6 is the presentation layer, which presents to upper layers like the application layer, but it also does encryption. And layer 7 is you using Microsoft Word or you using Microsoft Outlook for email. People tell me people don't use it anymore, but I use it all the time, or Microsoft Excel or what have you. So I kind of hope that makes sense. Now, generally speaking, and I'm teaching you this because it could end up on a test. We are in the world of classless interdomain routing. And what does that mean? It means we don't use the silly boundaries by IP classes. And by doing so, we can make efficient use. So realistically speaking, there's 5 classes of IP addresses, but we don't use them anymore, or we don't use classes anymore, but I want you to see them. So we wrote them down for you. Classless or classful addresses, meaning we adhere to these. If you note this 1.0.0.0/8 would be a class A address, as would a 2.0.0.0 all the way to 126.255.255.255/8. The class A range is ranged. Here's the thing to remember. There's 16 million addresses in a class A environment. And I'll show you in a minute why that would just be ridiculous and won't work. Now, the class B addresses are where that first octet is 128 and that last, and they end at 191.255.255.255/16. So when you're given a class B address, you've got about 65,000 IP addresses here. Now, when you're dealing with a class C address, oops, I don't know what happened here. There, I'm trying to put this back on somehow. Somebody put a wrong number there. No big deal. So when we have class C addresses, we're dealing with the 192.0.0.0 all the way to 223.255.255.255, but they're all /24s, which means you've got a total of 254 addresses that you could use. And class D addresses are used for what's called IP multicast. Very minimal multicast you can actually do through the cloud. Very, very minimal. But if you wanted to send something and have a bunch of users use it, you would be there. So why can't we use any of these silly class-based IP addresses in the modern world? Well, I want you to watch the subnetting video of ours to really explain this, because this is absolutely critical. And without understanding subnetting, for the most part, except for being a software developer, there's no jobs you could possibly do in the world without understanding it, because it's pretty important, especially if you're going to be dealing with networking and data center components. So let's say your PC has 4 network cards in it. Each one of these links and cards has to be on a different subnet. And why does this matter? Well, I want you to see this just for argument's sake, and then we'll get back to the content. If this was a what happened? 1.0.0.1/8. Guess what? I can't put any other. This link has to be on a different subnet. So right here, I wasted 16 million addresses. Mind you, we don't have that many of them. Now, let's say on the next link, I made this 2.0.0.1. I burned another 16 million addresses. Can't use them anymore because I can't more than, say, 500 systems on a single subnet. And now I put this 3.0.0.18. Now I burned and wasted another 16 million addresses for that port. And now I'm going to put this as a 4.0.1. And this was a Class A address. So now I burned 64 million IP addresses all on a single router with 4 ports. Now, granted, we may be able to realistically use 500 systems on each one of these subnets, so we can probably get 2,000 of the addresses used of the 64 million we've created. Now, let's look at it a little differently. Let's say this was 192.168.1.1/30. Now, how many addresses did we use? 4. Now, this next one will be on the next subnet, and this is why you have to understand this, and we've got an 8-hour video for you to watch. Now, this next one is going to be on the next subnet up, which is .5. We now burned 4 more addresses versus 16 million. I hope this is making sense of why this matters. Now, in this particular case, now we're going to put this on the next subnet, which is going to burn 4 more addresses. And now while we're over here, we're going to use careful subnetting, otherwise known as classless interdomain routing. And we've used a total of, guess what? 16 addresses versus 64 million. I kind of hope that makes sense to you with regards to inefficiency. Do you want to burn $64 million or $16? Same kind of concept. So nobody uses IP address classes anymore. We are now in the world of classless interdomain routing, which basically means we subnet it. And what routers do is they build a map of the network. They create a table, a database in the routers, and they determine how to get your data from point A to point B. Azure, AWS, Google, they all support classless routing. And I was using classless routing back in 1993 on Cisco routers, so it's not exactly a new innovation. Center. Your normal data center is this physical building where you put your stuff in, like your servers, right? Well, in the cloud, we don't have a virtual data center. We're renting a hotel room in that whole hotel. But it's not a physical hotel room. It's a logical hotel room. So we're creating a virtual data center, and we're going to put things like virtual machines and containers inside of our virtual data center. So the underlying network infrastructure, which would normally be routers and switches, are virtual routers and switches, and it's called a VNet. So we have to understand that when it comes to cloud networking, the cloud provider is a little bit funny. Normally speaking, we lose 2 IP addresses. And for example, if we had a 192.168.0.0/24, the 192.168.0.0 couldn't be used because that's the network address that the routers use to determine your destination. And we also couldn't assign to a host a 192.168.0.0.255, and we couldn't assign that one because that's the broadcast, which means every host has to receive it. So we normally lose 2 addresses. The first address, which is reserved for the network, the last address, which is reserved for the broadcast. But not with AWS, not with Azure. They reserve the first 4 IP addresses in a subnet. And of course, you can't use the broadcast. That means that you lose 5 IP addresses. So for the most part, the smallest subnet you could actually use in a cloud would be a /28. Here's the thing. Give yourself a /24 on average for LANs, because that gives you about 254 total addresses that you could use. And all in all, if you think you only need 10 servers, you'll need 250. So give yourself a /24. you could, Brett, when your network architects create your subnetting plan for most of your LAN subnets, potentially a /23, and use the smallest thing you can for your wide area network links. Normally we'd use a /30, maybe use a /28. Now, what kind of IP addresses could you use on your internal networks? Well, if we go back to my favorite place to get free and accurate networking information, the Internet Engineering Task Force, there's this document called RFC 1918, which specifies private IP addresses. Private IP addresses are stuff that's hidden from the internet. So where would you use it? The 10.0.0/8 is private addresses, the 172.16.0.0/12, and the 192.168.0.0/16. That is private addresses, and you can use these private addresses for systems inside of your VNet that will not be reachable from the internet unless you do NAT or connect them some way. Now, there's also this concept of the shared address space, and that is the 100.64.0.0, which takes us all the way to the 100.127.255.255/10. That's called the shared address space, so you can use it. So you can use the private address spaces spelled out in RFC 1918 and the shared addresses, which are 100.64.0.0, all the way through 100.127.255.255/10. Now, I wrote this down because I wanted you to see which IP addresses that were actually reserved. The 192.168.1.0 is still used for the gateway as the network address. But Azure also reserves the first IP address to be used by the router itself or the default gateway. Then they reserve the second and third IP address of the subnet to map to the Azure DNS space. And then obviously the last address is a broadcast. So they do some funny things with networking, and just keep that in the back of your mind. So here's some best practices. Use contiguous subnets. Plan ahead and save space. Use a bigger subnet that you think you need. Use a /24 or a /23. You want to reduce your management overhead by doing so with from a management perspective, it's going to be easier to have a bigger VNet and less of them. From a security perspective, you want more VNets and peer them. So kind of keep that in the back of your mind. So I said contiguous IP address spaces, and somehow I think most people won't know what that means. And I'll show you what I mean by this, because this will cause your architecture to crash and burn faster than you've ever seen. And one of the biggest problems I've seen is networking, is people don't understand networking. If a company doesn't have a dedicated network team, and maybe they have some Linux people doing networking, and they're also doing this, what you have is jack of all trades that really don't know enough about anything. And that's fine in a small business, and what happens is small businesses do that, and then they become a big business, and nobody set the foundation right or the networking right, and everything falls apart. And most of my life has been fixing broken networks where people didn't understand this, because it affects the way you route. So let's say this is your data center, and let's say this is Azure. If we were to do this, if the data center had 10.0.0.0/16, and inside of the data center, it was using these subnets, 10.0.1.0/24, 10.0.2.0/24, 10.0.3.0/24. I can send only a single route of this 10.0.0 into BGP to Azure, because I used contiguous subnets. And this can go all the way, to the 10.0.4.5, and this is going to go all the way to 254.0. Actually, I can go to 254/24, but you can see the point. all I need to send to Azure from them to reach me is 10.0.0.16. And if in Azure what we had was, say, 172.16.116.0.0/16 is the CIDR range, then, I could easily be in a position where I could have a 172.1.0/24, 172.16. Actually, make this 0 just for my math to feel good in my mind, even though both would work. /24, 72.16.2.0/24. See, this is going to work because all Azure needs to send for me is, hey, to reach me, I have access to the 172.116.0.0. This is the way it's supposed to be done. But when people don't know networking, what they'll do is they'll put this 10. And then they'll have a 172.16.4.5.0/24. I don't know what happened there. And let's remove this. And let's say we have this here as well. So here we've got a problem because this 172.16.5.6 is now sitting inside of this CIDR range. And that means we can still do it because these subnets are not being used yet. But that means that that the cloud itself cannot advertise the 172.16.0.0.16 because a lot of these routes are already over here. And that's what happens when people use non-contiguous subnets. They need to send more routes. And as you send more routes, your routing table gets bigger and bigger and bigger. And what happens when the routing table gets too big, anytime the route needs to recalculate, all the routers have to recalculate this entire database. Their CPUs hit 100%. What happens is the routers crash, and then it takes another 3 to 5 minutes for the router to come up on board, and then poof, your network is down for 5 minutes. And when they come up, they all recalculate and another router crashes. Or, maybe they don't crash and reboot, and maybe they just don't forward traffic for 30 seconds, or they lose their neighbor adjacencies and recalculate the routes. So if your IP routing is not done right, if your addressing is done wrong, everything will collapse and everything will fall apart. And that's why we're pointing you to our 8-hour subnetting webinar, because I want to make sure you're there. But what is subnetting really? It's taking an IP network and chopping it down into multiple little networks to maximize our address space. And that's realistically why we're doing it. Now, there are also some addresses that you cannot use in Azure. And here's the reason why. You're not multicasting for the most part on the cloud. So you might be able to join a group or push a group or use a GRE tunnel to get through the cloud, but you're not really going to multicast. You're not going to send an all-F broadcast, which is what this is considered, because it won't leave your local subnet. All hosts have this 127.0.0.1 address to that. You can ping your own computer and see that your IP stack is good there. There's this auto IP addressing link local stuff. And this is internal DNS. You cannot use any of these IP addresses. Keep that in the back of your mind. I'm going to briefly talk about supernetting, which supernetting and route aggregation are kind of the same. I just showed you how simple and elegant it would be to send a single route to Azure and a single route to the data center. So what supernetting is taking multiple subnets, contiguous subnets, and being able to aggregate them into something big. Or I've got like the 192.168.0.0/24 and the 192.168.0.1/24, and I summarize it around /23. I'll show you in a minute. But we're doing this to reduce the number of routes. It is not uncommon for an enterprise to have 10 to 15,000 routes in the routing table. But you can't send 10,000 routes to the cloud provider. You may only be able to send them 100 or 1,000 based upon the cloud provider. So you will have to be able to summarize your routes or supernet things along the way. And realistically speaking, what we're doing here is, and bear with me, sometimes people draw some photos for me, and this should be a 192.168.0.0. This should be the 192.168.1.0. This is the 192.168.2.0 and the 192.168.3.0. And this can be summarized into a single route or route aggregated or supernetted. I kind of to that 192.168.0.0/22. There's 8 hours of videos on that, so we can have you take it from there. Now, next, we'll talk about IPv6 addresses. So we're currently using IPv4. We've been using IPv4 or version 4 addresses since as long as I remember. And we're at the point now where people are starting to think about and potentially start to use IPv6 addresses. If you meet people that don't know networking, they're going to tell you everything's IPv6 because they don't really understand. Most things are IPv4. But we have a shortage of addresses. And with regards to the number of addresses, we have 2 to the 32nd power minus 2 for IP addresses via IPv4. And realistically speaking, instead of 2, we have 16 to the 128th power IP addresses via IPv6. So you can see that's a lot more. Now, we may use IPv6 addresses inside of a VNet. We can use them on virtual machine network interfaces, on internal load balancers, application gateways, or even the on-premise network with a VPN gateway or an express route circuit. And we can get our IP addresses either statically assigned, so it won't change, or dynamically assigned via, say, DHCP. By default, on the cloud, when you get an IP address, it is dynamically assigned to you. You're just given one. So you bring up your system, you're given an IP address, and if you don't want it, you can release it or delete that interface or reassign it to a different subnet. But you're typically going to be given an IPv6 address. It's allocated dynamically. You can also assign one statically. And by assigning it statically, you know exactly where it's going to be. Static addresses are only released if the interface or the network interface is deleted. So when you assign a network interface in a different subnet, users can change it from static to dynamic and what have you. Because static is going to be same and it's not going to move with you. So let's talk a little bit about IP addressing for different things, your VNets, subnets, network security groups, firewalls, and load balancers. When configuring a VNet, I mentioned this before, but I wrote this down because I wanted to be able to show it to you. These are your IP address spaces that you can use. Again, it's at 10.0.0.8, that 172.16.0.0/12, that 192.168.0.0, all the way through 192.168.255.255. The shared address space that you can see here is that 100.64.0.0, all the way to 100.127.255.255/10. That's your shared address space. And obviously, you can't be using the same address space at a different part of your network, or it won't work unless you use NAT to translate between them. What we do in networking is we create a subnet off of one of our routers, and that interface plugs into a switch, and the servers are plugged in here. In this case, we're creating subnets that exist in a virtual network. It's really the same thing. It's just virtual versus physical. Now, let's say we've got something that we actually want. We've got to protect it, right? So if I just put a machine out there right now, anybody that wants to access the machine can access the machine. So now I go to Kali Linux, I type in the IP address of your machine, I find all these vulnerabilities on the machine, and I can use Kali Linux to hack into your machine. Not so good, right? So there's a lot of things we need to actually do to secure our systems. One of the many, many, many things we have access to, and believe me, this is not enough by its own, but it's very helpful, is what's called a network security group. And that's basically used to filter traffic to and from Azure resources. So allow to reach this web server, permit unknown to reach addresses to reach web server at 1.2.3.4 on port 443. Now 1.2.3.4 is a public IP address, so I don't want to use that, but you get the concept, just making up an address. So don't go to look that IP address. So that's really what we're talking about. It's like a firewall, and then it's going to have security rules that allows inbound traffic or outbound traffic. So basically, you specify the source and destination addresses, the protocol, TCP, UCP, ICMP, and the port number, kind of just like a firewall. So what's a firewall? Well, there's all kinds of firewalls out there, and we'll talk about why the cloud providers' firewalls generally don't provide the level of security of enterprise-grade firewalls when we get to that section. But a firewall is basically a router that runs special security software that allows all your internal traffic to go out to the internet and come back. And it doesn't allow any traffic in unless you explicitly permit it. So if you guys want, when we get to the firewall and security section, maybe we'll architect a demilitarized zone for something like that, and I'm happy to do it. But that's kind of what we're talking about here. Firewalls. And basically they're filters. Now, good firewalls in today's world can look for patterns of behavior that don't seem to make sense, and they can block in real time. Actually, you know what? Maybe we'll do a little mini firewall thing here. Then we'll take a quick break. Remember, this week is fundamentals. Next week, we're going to go into the solution architect expert stuff. So let's say this device over here is my firewall. And of course, we need a user on a computer. So we're going to bring in my favorite user, little Cindy the cat over here. We have to protect Cindy. She's a very sweet little girl. We don't want anybody hurting her. So she's going to sit behind a firewall. And I'll show you the difference between, while we're at it, with real enterprise grade next generation firewalls versus the other stuff that's out there. Now let's bring our internet in here. And I'm going to sneeze just thinking about my cat. Bear with me 1 second if I can figure out how to. Okay, so now we have the internet. Cindy's favorite tuna.com. She loves tuna. It has to be fancy white albacore tuna. It has to be from one store. It has to look and be perfectly fresh. She's a little crazy with her tuna, but we love her around here. So all firewalls do this. They're stateful. Cindy goes to the internet. Her traffic goes through the internet and goes to Cindy's favorite tuna.com. Cindy's favorite tuna.com responds, and her traffic is allowed back in because she initiated it. By comparison, over here, we've got Hal the hacker. Hal the hacker tries to get past the firewall, and it is blocked. Can't go through the firewall by default. So that's typically speaking your firewall and the way your firewalls work. Now let's kind of take a different firewall scenario here, because there's lots of places you may want to use firewalls. Bear with me 1 second. Here might be the other place. We might have the internet over here. For my purposes, I typically think when we're dealing with unprotected traffic, we're going this way. So here we've got a firewall. Behind here we've got the internet. Now we're going to have a next generation firewall, which is why you're not going to typically use a cloud provider's firewall if your security matters. Off of the firewall. And there's going to be a lot more that goes into designing a demilitarized zone. Here's going to be the load balancer. On the outside of the load balancer is going to be a public IP address. I'll put a P on here so you can see that it's public. And maybe we've got a virtual machine web server here, so some web servers. In order to make this work, what do these web servers need to allow in to be reachable? And there's a lot more that goes into securing this than just a firewall. That's the kind of stuff we teach our architects in our training program. So What I'd have to do on this firewall is I have to allow TCP port 443, assuming we're using HTTPS, to the public IP address of load balancer. And what has to happen is I have to allow web TCP port 443 to come into this traffic here so they can go to the web servers and the web servers can respond. Now, what if a user is trying to come in on TCP or UDP on any port other than 443? The firewall will block it. Now, here's the difference between a cloud provider's firewall and the good stuff you should be using when it really matters. So right now, everything's going fine. Out of nowhere, and I don't know how this person does it, but you got Hal the hacker. And Hal the hacker is really, really good. And somehow Hal the hacker is sending some trade into this firewall. But the firewall doesn't like it. It doesn't know why, but something about it is scaring it. Kind of like if you went through airport security and something about you looks suspicious, they're going to know to try to frisk you, what have you. I get frisked all the time. I don't know why. But I travel so much. I got 1,000,001 stamps on my passport. So people constantly check me whenever I go through a security checkpoint. It's fine. It's no big deal. Hopefully they actually check for the real threats. But not business people who travel a lot. So in a next generation firewall, it doesn't feel right. Something's going wrong and the firewall is going to block it anyway. So the difference between an old school firewall is it actually has this intrusion detection, intrusion prevention, warning where things don't feel right, that next generation is going to stop it. Now, there are two ways that next generation firewalls can work. They can use signature detection and they can use anomaly detection. Here's what signature detection is. Somebody is using the same attack as Hal the hacker, and we know about that attack because we have signatures like your antivirus, and we're going to stop it. You may even get that on some of the cloud providers' firewalls. So, known attacks, you may get a benefit of it. But what happens if Hal the hacker is smart and Hal the hacker does something that nobody's ever done before? Well, a signature-based firewall is going to say, I've never seen that attack before, and you're going right through it. An anomaly-based firewall is going to say, well, this isn't supposed to happen. I don't like this. Let's act. Let's do something about it, and let's go fix it. So that is the big difference, which is why enterprises aren't going to use the cloud providers type WAFs when it matters. They're going to need that next generation firewall that's an industry-grade firewall. Chris, I believe, but I'm not sure. It's time to take some questions. So let's see if there's any questions before we get into the VNet. So I'll give you guys a couple of seconds to see if anything popped up. If not, I'm going to get back to talking about networking because I absolutely love talking about networking. While we wait for your questions for a few seconds, I'd like to remind you, we have a completely free set of labs for you to do on your own time. Go do these labs, get hands-on, and go have some fun. I also want to let you know that every Thursday we do a webinar on how to get your first job of some kind. It could be AI architect, cloud architect, enterprise architect. But whatever the case is, tomorrow's we're doing is going to be on cloud architects and solutions architects. Please join us. It's all completely free. My team will pop a link to that in the chat box, but we have one every week. Tomorrow's going to be at 11 a.m. Eastern, but we usually have them at 1 p.m. Eastern. But we want to be able to do the webinar, the free webinar, and the free training tomorrow. We like to have fun with these things. Well, I haven't seen any questions on this content come up, so I'm going to go back to the content. Give me a hashtag AZ305 so that I know that you're still awake and our Azure Solutions Architect expert training. One question did pop in, only one firewall can be used at a time. No, not at all. In a high security environment, we will use multiple layers of firewalls, and they will be different firewalls. So I know a lot of martial arts. It's been my life. And each martial art has its strengths. For example, edge weapon training, Salat out of Indonesia and Kali and Eskrima out of the Philippines are the best edge weapon fighting martial arts in the world. The best ground fighting martial arts in the world are Brazilian Jiu-Jitsu. And Muay Thai is great for competition. So You might want to have, as a martial artist, multiple skills. I've studied Krav Maga for most of my life. I did some jujitsu. I did some Eskrima. I did some Salat. I did some Taekwondo and some Shotokan. Loved them all. And they all made me better at martial arts. So we might have some firewalls from, say, Palo Alto, which are good at one thing, and some other firewalls from, say, Fortinet, which are good at another thing. And we may use multiple layers of different firewalls, the same way you may find a person in mixed martial arts learning multiple arts. It's the same reason, because each firewall has its strengths and weaknesses, and you really want to stop track. So we'll be using lots of firewalls, IDS, IPS systems, access control lists, network security groups, hardening our systems. We're going to be doing so many. So the next question you're just asking about Azure Firewall, that's the reason big companies don't use it, Michael, because it won't recognize unknown attacks. So do you want a firewall that's going to only protect you from known things? Or would you use a firewall that's going to protect you from the unknown and the unknowable? And that's why nobody that's serious about high security environments is going to use the Azure Firewall or the AWS WAF. For the most part, and it's not going to work in a multi-cloud environment anyway, we should use a standard set of tools and a standard set of firewalls. So no big companies that matter are going to ever use any of these cloud security services like their firewalls as primary security. You've got to look at security, and you've got to look at the difference between a jack of all trades and someone that's an expert. Palo Alto makes great firewalls. Fortinet makes great firewalls. Checkpoint makes great firewalls. All those companies do is focus on security. So you want to get your security from a security company, or do you want to get your security from a company that makes cloud services, operating systems, video games, those kind of things? That's why big companies typically use enterprise-grade firewalls. And that's why we teach these programs different, because I don't want to just tell you, here's your AWS stuff or your Azure stuff, and it's what you should use for everything, because it's not. And, the wisdom is knowing what you should use and what you shouldn't use, and the why for your rationale. Great question. All right. So now we'll get back to the content over here. We'll start talking about the VNet. The VNet is your virtual data center. And it's that virtualized version of an on-premise network, but, now it's logical instead of physical. It is where you put your stuff. So inside of your VNet, systems can communicate with each other. Inside of a VNet, systems, typically speaking, can communicate with each other, which means if you want high security, you may take your network and break it down into multiple separate VNets. And that way, some systems can talk to other systems. In the data center, we create multiple virtual LANs that we control where our routing is. In the cloud, we can use access control lists or network security groups to limit it, just like we do in the data center. But we also have the advantage of being able to logically separate our networks, because that gives us one layer of security. And security, you want like an onion, where you peel back a layer and there's another layer and another layer, or those Russian dolls where it's a big doll and you open up and there's another doll inside, and you open up and there's another doll inside and there's another one. It's kind of cool. My grandmother used to have them. But the point is, no one layer of security is ever going to be enough. So we may isolate our systems into multiple VNets for security, and there what's called VNet peering between them. But the VNet is between your Azure resources. You can connect your physical data center to your virtual data center called VNet. We can route our traffic in the VNet because it's got virtual routers, because we can't get traffic on and off of our subnets without a router. And it integrates with our Azure services. So now we're going to talk about virtual network NAT. What is it? Well, every device needs to have a different IP address. So one of the types of NAT that we actually use is what's called port address translation, otherwise known as NAT overload. This is what most of you are actually familiar with. So you work at a company, you sit behind a firewall, you've got a private IP address, and they translate your private IP addresses to a single or a couple IP addresses that are public for the company. That is port address translation, otherwise known as NAT overload. And that's typically we're talking about virtual network NAT. But understand here is another use case of NAT. Company A is using the 10.0.0.0/8 address space. Company B is using the 10.0.0.0/8 CIDR range address space. Company A buyers Company B, and now they've got the same IP addresses. Their systems can't talk to each other because they have the same addresses. So they may use NAT to translate one addresses to a different address and another on the other side. So that would be another case for NAT. But right now we're talking about NAT overload, otherwise known as PAT, port address translation. So we're using this because we want our systems on the internal network to go out to the internet, maybe for patching their operating systems or reaching the internet. And we want their traffic coming back, but we don't want them reachable from the internet, which is why you can be behind a firewall. One of the reasons you can go to the internet and nobody even knows your real IP address. They see the IP address of the outside of the firewall. Kind of hope that makes sense. Now let's talk about a VPN gateway. We'll talk specifically about the Azure VPN gateway. So if you're going to connect to something, what are you going to connect to? So if I want to, let's say Alonzo, I keep using Alonzo because he's been here most of the time. He drew a lot of these pretty pictures. The ones that I'm sharing, if they look pretty. If it's me, I basically don't use slides. I have a couple things that says, Mike, talk about a VPN gateway, and I just obviously know what to talk about because it's been my life's work. And but if I'm going to create a VPN between my house and Alonzo's house, I have to connect to something. That something that I connect to is typically speaking going to be his firewall or his VPN gateway. And if you're going to use a VPN to connect to Azure or connect one thing to another, you're going to need a router that can do the VPN work, that IPsec encryption that can terminate your connection. So the Azure VPN gateway is a virtual router / firewall that's used for you to connect to. And each VNet can have one VPN gateway, but you can create a whole bunch of connections. So let's see if that makes any sense. Maybe I'll show you what I mean. So let's say that I am here. This is Mike's house. Actually, I'll use Azure. And I want to connect to Azure, or specifically my VPC, and we're both connected to the internet. What I'm going to do is I'm going to create a tunnel between my router, which is called the gateway. That's the other word for a router. And the Azure router, which in this case is going to be called the VPN gateway. And I'm going to create a tunnel between these two things. That's what needs to be terminated. So that is a point-to-point VPN. Now, Azure will only allow you to have one VPN gateway, but it would enable you to have multiple connections. So now over here, we've got Chris's house, my chief operating officer. And Chris also needs to connect to the systems in Azure. So what he's going to do is he's going to have his router, and his router is going to connect to the same different VPN gateway. So that's really what we're talking about when we're saying each VNet can only have one of these, but multiple devices can talk to this. I kind of hope that makes sense. So the VPN gateway, when we're dealing with Azure, is going to be 2 or more virtual machines that are going to be automatically configured and deployed to your subnet when you create a gateway subnet. And it's going to be utilized to create these IPsec connections for your encrypted traffic between your on-premise location and your VNet over the public internet. Okay, now we're briefly going to talk about DNS. I am a network architect, an enterprise architect, a cloud architect. Typically speaking, DNS is done by sysadmins and PC type people. So this is not my biggest strength in the world, but I've still worked with it enough when we're going to talk about it. So DNS is really mapping a name to an IP address. Why do we do that? And every one of you, if you have a command prompt, can you get to a terminal window or a command? So on Windows, open up a PowerShell, for example. On Linux, just open a terminal. On a Mac, open a terminal. And let me see PowerShell. And in that PowerShell Windows, if you're on Windows or Linux terminal, I want you to type in NSLOOKUP, NSLOOKUP, www.cisco.com. You're going to pick Cisco. Now, you're going to see a couple things when you do this. First thing is you're going to see your DNS servers. Mine happen to be 8.8.8.8 because I use Google's DNS servers. Then you're going to see this name. And, depending upon where you're at, you're going to get it. For me, my name is Echo 2867 Delta Sierra Charlie Alpha .akamaiedge.net. And that actually underneath it has some IP addresses that you could reach. It's got some IPv6 addresses. It's got some IPv4 addresses. And why is this? Am I really going to remember the address 2600:1403:9 Charlie 00:1287 Bravo 33? No, but I can remember Cisco.com. And that's why we use DNS, is to map a name to an IP address. So hope you had a little fun doing a little bit of hands-on work there to try to figure out the domain name. You can do an NSLOOKUP of Microsoft and NSLOOKUP of anybody, and you'll see the name IP addresses that are matched with the name. Now, when we deal with addresses, we have to have when we're connecting to something, we typically speaking have what's called a fully qualified domain name. And a domain name is the name of the domain you're looking for. Our domain happens to be Go Cloud Careers. It started as Go Cloud Architects because we were only training cloud architects. And the next thing you realize, we're training enterprise architects. And with David Lithicum, artificial intelligence architects. We train lots of security architects. So we changed it to Go Cloud Careers, what have you. The point is Go Cloud Careers is our domain name. Now, I might name my PC, if it was part of it, mikepc.gocloudcareers.com. That is also what's considered a full domain name, in that it's going to have a host name, a domain name, and then what's called a top-level domain. So let me kind of draw this out for you. In this particular fully qualified domain name, www.gocloudcareers.com, www in this case is going to represent what would be the host name. It could also be mikepc.gocloudcareers.com, but the host name in this case we're talking about is www. The domain name is Go Cloud Careers, and the top level domain is .com. Now, a top level main domain could be .org, .edu, .net. So that's your top level domain. So when it comes to DNS, there's a couple ways you can do it. If you have 3 different clouds, you better manage your own servers and maybe go to F5 and have DNS servers across a lot of cloud providers. Because if you're just using Azure DNS and Azure goes down, then your systems in AWS and Google aren't going to work. If you just use AWS Route 53 and that goes down, then your systems in Azure and Google won't work. So generally speaking, if you're multi-cloud, you're going to manage your own DNS. But if you don't want to manage your own DNS and you're only dealing with a single cloud and you don't really have a lot of availability concerns, Azure has their own DNS for you, like AWS Route 53. And it's a very scalable, very low cost, very easy to set up and use DNS system. And it supports IPv4 and IPv6. It also supports health checks, which we'll get to at some point. And it can route your data inside Azure or other places, including AWS, unless it goes down, which is why, generally speaking, if you've got more than one cloud, you probably need to manage your own DNS. Azure DNS gives great performance. It's got a very high availability system. It uses Anycast, which means if the local one you reached and went down, another one will be able to answer it. DNS queries are answered by the closest available service. It is a rock solid, great DNS service. along with AWS Route 53, etc. These are great, but single point of failure if you got multiple clouds. Or they were to get hacked or have major issues. So Azure DNS will support, your main record types. I'm going to share this because I prepared these. So these couple of slides. So it'll support an A record. That's your simple record. Basically, that maps Cindy.com to whatever her IP address is. We'll have an AAA record with 4 A's, which is the same thing as an A record, but for IPv6 versus the A record, which is IPv4. We may have a CAA record, which is related to our certificates. We may have a scene name record, map Go Cloud Architects to Go Cloud Careers. And that way, if you went to www.gocloudarchitects.com, because you saw one of our older videos when we were Go Cloud Architects, when we were smaller, you'd automatically be sent to the Go Cloud Careers website. And of course, we have a scene name record for that. While we're actually at it, let's see what else we're talking about here. We're going to have an MX record, which is going to be necessary if you want to send and receive email. We will have a name server record. We will have a PTR record, a startup authority or zone record, and a service locator, as well as something called a text record, which is going to have a lot of the information we have. So DNS records, you may hear them called zone files. What they really are sets of instructions that are going to be in your DNS servers that's going to provide the information on the domain. Now, these records are going to be in a particular format. It's typically called DNS syntax, which is really a text record. And the DNS syntax is going to tell those DNS servers what to do and how to do their job. They're also going to come with something called a TTL, or time to live, which is how long it'll take until DNS refreshes the records. Meaning if the TTL is 1 day and you change something, you may not notice it for up to a day. Longer the TTL, more scalable your DNS is. Longer your TTL, the longer it's going to take for failures and updates kind of to update their way through the system. Now let's talk about Azure Traffic Manager. What is that? It is a DNS-based load balancer. So maybe you want to send half of your traffic to this region versus this region, or half of your traffic to AWS or Google if you're going to use this, and that's the Azure Traffic Manager. Send half of your data to your data center or a private cloud, whether it be a VMware cloud, an Nutanix cloud, an OpenStack cloud, send the other 50% to AWS. That's what we're talking about, the Azure Traffic Manager. It's a DNS-based load balancer. And it allows you to send your traffic to multiple regions, gives you public endpoints, and it does high availability by checking to make sure systems are there with a health check. If they're not there, they reroute it. It will give you increased application availability, improved application performance. It'll give you the opportunity to do maintenance on a system without downtime because it'll just reroute your traffic. And the way it typically works, it selects an available endpoint in an Azure data center with the lowest latency for that IP address range. And it's going to distribute your traffic evenly across endpoints based upon the way you set the policy. And it'll typically reroute your traffic to whatever's the closest to give you the best performance, closest location. Now, with Azure Traffic Manager, we can set up a whole lot of different kinds of routing, meaning how do we send our routing? So we'll talk about priority routing, weighted routing, performance-based routing, geographic routing, multi-value routing, and subnet-based routing. Here's what priority routing is. Send all your data to your data center, and if that fails, send it to Azure. Send all your data to Azure, but if it fails, go to AWS. That is priority routing. Now, you can see why that would work. The next type of routing is what's called weighted routing. Send 50% to AWS, send 50% to Azure. 50% to AWS, 50% to Azure. AWS goes away, send 100% to Azure. Azure goes away, send 100% to AWS. Weighted routing, great. And think about this from a high availability perspective. 50% of my traffic's at AWS and 50% to Azure, and they're all in auto scaling group. Azure goes down. Remaining traffic is 50% of your traffic is already going to AWS, and then auto scaling, and all of a sudden AWS takes over the entire load. So this kind of multi-cloud stuff, it's really simple. It's only that if you don't know networking, it seems complicated or scary, but it's really simple. The secret is having good networking people and not using proprietary stuff, and then you're good. Like the proprietary databases, use stuff that works everywhere, and you don't have any of these problems. They're usually better services anyway. Now, performance-based routing is going to be a little different. That's the least latency. So let's say I'm in Greece, for example, and I could be sent to New York, or I could be sent to Stuttgart, where our website is hosted. Well, Stuttgart in Germany is a whole lot closer than, say, New York. So if the latency is less to Stuttgart, in performance-based routing, it's going to send me from Greece to Stuttgart. And if Stuttgart is down, it's going to send me to, say, New York. So that's performance. So priority, pick one place. Weighted, pick a weight. Performance. Here's another place where you may, so going back to weighted, here's another use case that you may think of from an architectural perspective. Your team wants to deploy a new public-facing website, right? You got your old website where you're sending 90% of your traffic. Use weighted routing to send 10% to your new website. If the new website crashes, don't worry, you go back to your old website. Life's good. If the new website works and people start to use it and it's reliable, with rated routing, then send 20% to the new website, then 30%, then 40%, then 50%, and send it all over to the new website and remove the old website. So you see why we use priority. We've discussed a couple of use cases for weighted, and we talked about performance. Now, geographic is going to be based upon geographic, and it's going to send you to specific endpoints based upon where you're at, the IP address of your origination. So think about this. You're now in the country of Cyprus. Great country, beautiful place. There's really two primary languages in Cyprus, Turkish and Greek. So if you're on the Greek side of Cyprus, maybe you get the Greek-facing web page. But if you're on the Turkish side of Cyprus, based upon your IP address, maybe you get your website in Turkish. That's typically where you're speaking geographic. Think about countries where there's 4 and 5 languages spoken, or a region where you could be speaking French or Arabic or so many languages or other languages. But if you get the language of your choice based upon where your IP address is, usually is going to be the best option. And then there's this concept of multi-value. I hate multi-value DNS. Multi-value is, here, we're randomly going to figure out where we're going to send your stuff. I don't like that. I want to know where my stuff is going. And subnet-based routing is basically speaking, it's going to send it to a specific subnet until proven otherwise. We may use Traffic Manager to migrate to a new application. Like I said, that kind of environment where you send it to a trial web page versus the original one. We can use it to basically send all the traffic to our data center. Because remember, the data center is going to give us better performance. It's going to give us lower cost for frequently running workloads. And if the data center gets busy, shoot it over to Azure and expand and create all these virtual machines on demand. So really good use cases for this. But all in all, it is a DNS system. So how do you compare Azure Traffic Manager versus DNS? If all you need is to map a IP address to a name, Azure DNS is your option, assuming you don't manage your own. By comparison, Traffic Manager is going to be if you need a high availability setup, if you need to do some performance-based things. So that's realistically speaking what we're talking about. All in all, Traffic Manager is going to enable you to do more things. But you can manage your own DNS systems. You get some great DNS servers from, say, F5, and then pop them in all clouds, and you don't have any of these things. So now I talked about health monitoring, and I really want to show you what that is. And health monitoring is going to be this, and this is really important. Our load balancers can do it, and our DNS can do it. So we're going to talk about health checks and health monitoring. So for right now, let's pretend DNS is this pie in the sky thing that's over here. Here's your DNS. And this is going to be AWS. And this is going to be Azure. This is a traditional, enterprise that we would be dealing with right now. They'd also have their own data centers. So we might have a weighted routing policy where 50% AWS, 50% Azure. And what's going to happen is under normal circumstances, half of the traffic goes to AWS, half of the traffic, oops, didn't mean to do that. The other half of the traffic goes to Azure. And life's running, everything's good. Now, every couple of seconds, Azure sends a message, the DNS sends a message to Azure, are you there? And Azure says, of course I'm here. AWS, I'm here, I'm having a good time. Then the next thing you realize is DNS sends a message to Azure. Azure, are you there? Yeah, I'm here. It sends a message back. Kind of like when you're in homeroom and they asked if you were there and you said you were. Otherwise, they marked you out of class and you got a detention or something like that. Then it checks on AWS. Are you there? Yep, I'm here. Checks on Azure. Are you there? Yes, I'm here. AWS, are you here? Yes, I am. Azure, are you there? Then out of nowhere, a message gets sent to Azure. Are you there? And Azure doesn't respond. The next message goes to AWS. Are you there? Yep, I'm here. The next message goes to Azure. Are you there? No response. This isn't good. Another health check goes to AWS. Are you there? Third message goes to Azure. Are you there? And these are 3 or 4 messages typically the way these work. No response. Azure is now unhealthy. Azure is no longer usable. It failed the health check. Send all traffic over to AWS. So now all your traffic's over in AWS. And guess what? Your virtual machines for your website are in an auto-scaling group. So now your website, your virtual machines expand, and now your systems are up and operational at 100% capacity in the next cloud over. There's some time for auto-scaling to work, but that's what these health checks are. So we talked about these routing policies that we could use on Azure DNS. All right, so I'm going to talk about load balancers, one of my favorite high availability devices, and then we'll probably take questions and end after that. So what's a load balancer? Well, a load balancer can be a hardware device or a software device that distributes traffic. Why do I like load balancers? Why do I love them? Well, they increase performance and availability. Which do you think is going to be greater availability? 5 servers or 1? Well, without a load balancer, we only have the ability to send our traffic to a single server. The load balancer is going to send traffic to multiple devices, and it's going to run that same health check that we talked about with regards to DNS. And by doing so, the load balancer will only send the traffic to the healthy devices. Pretty cool, huh? So load balancers increase performance by allowing you to add extra servers or extra containers and also make sure they work. So they remove single points of failure and they increase performance. Now, typically speaking, we have 2 kinds of load balancers, and they're basically network load balancers and application load balancers, and there's a time and a place for each. A network load balancer is really, really fast. It looks at the TCP, the source and destination address, the protocol TCP, UDP, and the port numbers. And it just, traffic goes in and poof, it's out. It's in, it's out. It's in, it's out. And it's fast. Why? It's only looking at the header of the IP packet. Doesn't take that much work. How fast can you do math? 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30. Doesn't take much. I'm only adding 2. Because the network load balancer isn't doing enough. Now, by comparison, the application load balancer is smart. It's not going to just look at the TCP source and destination address, protocol, and port number. It's going to look at layer 7 into the headers. Is it an HTTP or HTTPS request? Is it being routed via push or get? It's going to be really smart. And application load balancers are relatively slow because they're smart. So if I asked you to calculate a derivative in calculus or something, except for my wife, who's how I know she can do it in her head in about a second, it's going to be slow because the rest of us humans, other than my wife, are going to have to figure out how to do it, calculate it, write it all down, and run the manual calculations. So kind of think about that. My wife's a math genius. It's kind of cool to see. Me, I don't like math. She's great at it. So we she doesn't love to give presentations. So we find a way to work together. That's the secret. Find people that are good at the stuff you're not good at, especially in your architecture teams. So application load balancers are slow. Now, of course, we're in the cloud. And of course, cloud providers can't really let you know what they really have. So they got to make up funny names. So the application load balancers are called application gateways in Azure. And network load balancers are considered Azure load balancers. I didn't make these marketing terms up. We also have two kinds of load balancers. Public load balancers are internet-facing load balancers and private. So I might have an internal application in my private network or intranet where I need to load share across 10 servers. That's a private load balancer. I may have a load balancer or multiple load balancers in front of my website to the world. That's a public load balancer. So public load balancers are going to be outbound connections for your virtual machines for externally facing things like website. And they will provide outbound connections to the virtual machines inside of your VNet or whatever your things are. Generally speaking, the load balancer itself will have a public IP address on the external side and an internal one for your servers, which means they're doing that at the same time, translating your private addresses to public addresses. Whereas private load balancers are inside of your systems. They use private IPs, generally speaking, at the front end. And they're used for load balancing inside of your systems. Now, going into there a little more, you've got the application gateway, which is the application load balancer. That's got all kinds of stuff and all kinds of intelligence in how it routes. And it supports things like SSL termination. So basically, you can run SSL encryption on the load balancer versus your devices, which means it offloads a lot of the work. Encryption's a lot of work for the CPU or the brain of your systems. So put it on the load balancer versus your systems, you save CPU resources. You can do things like affinity, round robin, send to each one, cookie-based sessions. So there's lots you can do with these things. So the next thing I'm going to talk about is the routes and routing table. So what on earth is a routing table? So when we have routers, they basically have to map. They have a map, and they build a map to get us from point A to point B. So if you're here on your PC, and you want to get to a web server, let's say your PC is connected to a router, which is connected to another router, which is going to be connected to another router. Your router that you have is going to be attached to an Ethernet switch. And over here, you're going to have the server. So let's say over here. Okay, this router is linked over here. So here's your PC, and this is the way routing is going to work. And we're going to discuss routing and routing tables at the same point. We have a free CCNA program that will on our channel that will explain much more, but let's just do this for right now. So remember, each one of these links has to be on a different subnet. So assuming all these routers are running the same protocol, this link has to be on the same subnet as the PC. So that could be 10.0.0.1. Now, here we're going to use a wide area network segment. So let's, and we're going to be terribly wasteful in address space. I want to make it clear. Let's say this is 192 192.168.1.1 on this side of the link. And then the opposite side of the link has to be on the same subnet. And this is going to be a /30. And over here, this is going to be on this side of the link. It's going to be a .2. It's going to be on the same subnet. /30. And then what'll happen is on this side of the link, it'll be on a different subnet. So this can be .5. And on this side of the link over here, this will be, let me copy this. It'll be .6. And then, of course, this link on this subnet is going to have to be on the same subnet. So let's make this .1. So the way routing is going to occur is the PC is going to say, I want to reach server named A. And it's going to look on it. It's going to look in its routing table. And what the PC is going to have is it's going to have a link to this 10.0 subnet. And it's going to have a default gateway, which basically says, if I don't know where to go here. Now, when the packet so what's going to happen is the PC is on Ethernet. So it's going to send it's going to ask who has the MAC address for 172.16.1.0. This router here is going to respond to that. It's called the proxy ARP. And it's going to say, I have the MAC address. Now the packet reached this first router. And when the packet made it to this router, it says, do I have a route in its routing table to 172.16.1.6? And it says, yes, use this Ethernet interface. And then the router is going to say, who has the MAC address of 172.16.1.0? This router will respond with the proxy ARP. Now the packet made it to this router, and the router is going to say, who has the MAC? Do I have a route to 172.116.1.6/0/24? And it's going to say, I sure do. Send the packet over to here. Obviously, it'll respond to the ARP request, and then it'll be sent out this packet. So what happens is these routers run what's called the routing protocol. And it's going to say to reach, let's say this is router 1. Router 1 will say to reach 172, let's say this is Ethernet 1. Let's say this is the Ethernet 1 port. Let's pop this over here to make it clear. E1. To reach the 172. And it's going to have these in its routes and routing table. So it's going to say to reach 172.16.1.0/24, use port E1, meaning send it out this link. To reach, and it'll be its routing protocol. To reach the 10.0.0.0/24, let's make this port E2. To reach this subnet, the .4, let's pop in all our subnets. This is going to be /1.0/30. That's on E1. And then to reach the 172.1.6, or I'm sorry, 192.168.1.4/30, use E1. And then, so that's what it's going to be in a routing table. And this routing table will basically tell this router, how do I reach these various subnets based upon the table? When I go to the 10 subnet, go this way. Now, each one of these routers will have their own routing table, which will tell them how to get to every single subnet. But we just designed and created a routing table in about 5 minutes live. So that's really what we're going to do. We're talking about. Now, the next thing I want to talk about is something called private link. And what is private link? Well, there's going to be some things that are inside of your VPC, other things that are going to be not. Now, you could, go from your VPC across the public internet to connect to something else. Or you could leverage the IP connectivity that you would be using. And leveraging the IP connectivity that you might be using could be done over the Azure network. So basically, they're going to create you a virtual link, as if you've got a virtual private line. And it's going to be tunneled over the Azure network in a secure manner. And private link is going to be a service that can be accessed from any of the approved private endpoints in your region. It's basically a network interface, and you're going to deploy it in the same region as the virtual network that you have in your load balancer. And private link is going to be a means to attach to somebody else. It's a virtual link, if you will. It's a virtual private line, and it's going to keep all traffic between your VNet and Azure or the customer or partner gateways that you're using. And it's going to look something like this. You could have, say, your on-premise somewhere subnets and network that's connected via this private line or access route. You've got this private endpoint, and then that's going to take you to, say, a various VPC of maybe somebody that's servicing you something. So it's really just a virtual private line. See, what you have over here, this express route, is a physical private line, but basically they're creating a private line over them. So they're creating an overlay, what's called a tunnel network. Actually, I'm going to cover service endpoints while we're at it, and then I'll take it to questions, and then we'll finish up for the day. So let's talk about service endpoints. So if you need to connect to something, you have to connect to something. So in the physical world, I connect to a router. But in the cloud, they're physical servers, but it's running all this fuzzy cloud software. And what are you really going to connect to? You can't really put a physical router there. Their routers are doing their infrastructure, and it's hidden from you. So an endpoint is a means to connect to the device itself. And that's really what we're talking about. So it's a logical interface. And you might connect your private link to an endpoint, and it's going to give you a secure virtual private line over the Azure network, leveraging the Azure Virtual Network. And there's lots of endpoints, because there's going to be some things that are in your VPC, like your virtual machines. But other stuff like Azure Storage or some of these databases are going to be outside your VPC. So you're going to have to connect to them securely. And that's typically over endpoints. My team made a list of some of these endpoints for you to think about: storage, some of these databases, Key Vault, event hubs, your data lake, cognitive services. So there's lots of things you can connect to over an endpoint. But the point is these are high availability, logical things that you can connect to, because you got to connect to something. And this is going to enable private IP addresses inside your VNet to reach an endpoint. It's going to enable reserved public IP addresses that are not required. And you're not going to need any NAT or gateway, because realistically speaking, it is a virtual gateway which comes as available to you as part of your Azure systems. So here you can see how it might work. You may have your virtual machine. You may be connecting to a endpoint service, and to be able to reach something inside of the Azure network, like blob storage, for example. Chris, why don't I take some questions, and I think we can end the day on questions. How does the reverse TLS connection work? So typically speaking, a TLS reverse connection is going to work by establishing a secure connection, which will be initiated from the server to the client instead of the client to the server. The server will connect back to the client. It'll use TLS to encrypt the data during its transmission. And this way it ensures confidentiality and integrity. It's often used in scenarios where the client is going to be behind, say, a firewall or NAT, and it'll make inbound connections relatively difficult, typically speaking. Chris, we can go to the next one. I thought you cannot route 192.168 over the public internet. That is 100% true. We can't route it over the public internet. But what I was drawing was actually a private network called an intranet. So generally speaking, inside of your systems, you're using private addresses. And guess what? The routers run routing protocols. Typically inside your systems, you will run an interior gateway protocol such as OSPF or intermediate systems to intermediate systems. Most enterprise customers will run OSPF. When we start getting into internet service provider design, we may use that. We can either use single area OSPF, or we could be using intermediate systems to intermediate systems. Intermediate systems to intermediate systems tends to scale well in a very flat network, the way it handles its LSAs. So often, if we're going to create an internet service provider, we could use OSPF, but we often use that intermediate systems to intermediate systems. And then we add some label switching protocol like MPLS, and we typically add some RSVP, and that's how we can create virtual networks over our private networks and guarantee performance. But absolutely, you're correct. You cannot route these over the public internet. But that's the difference between the intranet or the internet. Give me a minute to see if you have any others, and maybe, just maybe, we finish a few minutes early. We may have to run late on one of these days, just a little bit, depending upon how we progress. Let me see if there's any more, because the next section is VPC peering, and I want to give it the due diligence and time it absolutely desires. No others? Thank you for your comment there, Kevin. See, the question came from Michael. What is the equivalent of a VRF in Azure? So all of it's kind of the equivalent of the VRF. So for those of you that don't know, on Cisco, we have the ability to create virtual routing and forwarding instances on the router, effectively virtual routers on the router. Well, cloud computing is a virtual data center inside of a physical data center. So all of cloud computing effectively and all your VNets are the equivalent of a VRF. Cloud computing is pretty much all that, which is a really great question. Well, what I'll say is this, and see if any questions pop up. Join me tomorrow at 11 a.m. Eastern. My team you can use a time zone calendar. We're going to really talk about how to become a cloud architect. And while the majority of it's going to be cloud architect related, if you've got questions on any other career, I am really happy to answer them. It'll be on live. We'll talk about what we do, how we do it, and kind of keep that in the back of our mind. So pop the link immediately in the chat box. Come join us. And I'd love to see you. I'd love to answer any questions you have. Love to do anything I can. It's free to help you in your cloud computing career. So you can click on it. You can get set up reminders for my team. Set that up for you. Mike, please connect DL and data warehouse. Valerie, you know me. I don't know what you mean by DL. Do you mean data link? Do you mean download? I'm not really sure what you mean. Maybe it's data lake versus data warehouse. Okay. If it's data lake versus data warehouse, let me kind of describe it. Data, and my team helped me with that, Valerie. So data lake is basically where you put all your stuff, unstructured data. So in the data lake, you're pulling your information out of your data warehouse. You're pulling it out of your NoSQL databases. You're pulling it out of your relational databases. And you're pulling it out of object storage. You're going to normalize the data, and then you're going to save that data for something else, maybe some machine learning. By comparison, a data warehouse is really a database. So you're going to pop all your information in the database, and it's going to be structured data. So data warehouse, structured data, big giant database that scales. Data lake, taking your stuff from all your data sources, sticking it in object storage, and leaving it there in raw, unprocessed form, but normalized form for you to use later? That's a great question there, Valerie. Sorry, I didn't understand the uh, acronyms there. A lot of things sound in the same in functionality, like subnetting, BGP, routing tables, VPN. Well, subnetting is related to how you take your IP addresses and plan your IP addressing scheme. BGP is how you build dynamically your routing protocol when connecting to external entities. Just like it could be also created via static routes, which wouldn't scale very well, or OSPF, or an interior gateway protocol. The routing table is how you get to all the locations. VPN is tunneling information through the internet, and private lines is buying a wire. I don't really see them as similar. In fact, I can tell you that I spent almost 10 years learning and mastering BGP, but I was able to learn subnetting in about 4 hours. The whole concept of the routing table, I learned fairly quickly because it was easy. VPNs were fast. You can learn them almost overnight. Private lines, you can learn pretty quickly. So you're not going to necessarily get all this from the first time you watch this. It's going to take multiple times. It seems easy when I say this. And it seems easy because this has been my life's work. But understand this did not come overnight. So they sound the same, but they're nuanced, they're different. It's kind of like, the heart does what it does, which is pumps blood. The arteries take blood from the heart and distribute it from the body. The veins, for the most part, take the deoxygenated blood and send it back to the heart. And the lungs actually oxygenate the blood. Now, that's the cardiovascular system, and it all sounds the same. But you've got a problem with your lungs, it'll stop your heart. You've got a problem with your heart, it'll stop you from breathing. So they're all interdependent, interrelated. But the fact that you're starting to see the trends and where these things get together, this is a good thing, Freedom Lands. You wanted to get into cloud IoT. Can I get some insight related to me from this field? Yeah. So I'll invite you to the webinar where we'll talk tomorrow. But understand IoT is a networking specialty. And anything in networking is going to be a lot more complicated. So come to the webinar tomorrow because you can be at IoT as we're talking about the application side, IoT from the networking side, for example. But in order to understand IoT, you're really going to have to master networking, assuming you want to do it from the networking side. That means CCI equivalent networking knowledge. I don't care about the certification. You're also going to have to learn the idiosyncrasies of these IoT devices and the way they work. And you're also going to understand how these systems need to be controlled. Understand that a lot of IoT will be in the data center, a lot of it will be in the cloud, a lot of it will be in edge locations. But if that's your thing, master networking. And I love networking. But I would look at IoT and I would remove the word cloud. Because IoT is IP-enabled devices that are going to connect back to a data center. And it can be a physical data center or it can be a cloud data center, but it's more about learning IoT versus the cloud. Join us on the webinar tomorrow and we'll talk about it. I'll bring in some more people that are good with IoT, maybe two, to join us. Can I explain the lack of segmentation capabilities in clouds such as VLANs? Yeah. The cloud, the physical network enables you to isolate all these places. I got a switch. I can create a VLAN. I can, on my switch, make sure two devices can't go there. In the cloud, can you pop your own switches in? Nope. Can you pop your own physical firewalls in? Nope. Can you pop in anything you want in? No. So basically speaking, what we have in the cloud is the virtual software-based version of the real thing. And because it's a software-based version of the real thing, we don't have anywhere near as much features and functionalities as we do in the actual real thing. So we can't segment the same way. We can't do private VLANs. We can't do things like 802.1x type admission control. We can't run quality of service. So when we look at the networking capabilities of cloud computing, it's about where Cisco was in 1998 to 2000. We're lacking, and we even had those capabilities back then. So don't assume you're going to have on cloud equivalent functionality as the data center. The data center will always give you more capabilities, but you have to know it, you have to manage it, and you have to pay for it or finance it. So it's about using the right tool for the right job. But if you need extreme security and ultimate control and greater performance, it's going to go in a private cloud like Nutanix, OpenStack, or VMware. That's the reason why. Because you don't have, and the reason is when you connect to a cloud provider, they've got to connect to thousands or hundreds of thousands or millions of customers. So they have to be much more like that McDonald's, where they've got policies, procedures, and access. Where when it's in your own data center, you can do whatever the heck you want with it. In your own house, you can paint a wall yellow, green, and purple and orange. But the cloud provider is going to use the color that people are going to want to buy from a marketing perspective. So that's the reason. I hope that makes sense. Oh, Valerie, thank you. Mike, much appreciation for your time and sharing gradual knowledge that makes the great architects. Thanks so much, Valerie. It's always good to see you, Valerie. Hope to see you in person someday soon, too, because it's always great to see you. All right. Take care, everyone. Give me a hashtag AZ305. Join us on the free webinar tomorrow and download some of the free documents that are sitting inside. If you're new and you sometimes feel lost, Foolish the Crow, that's an interesting name. It's okay. You're going to feel lost because we're covering, honestly, 5 or 6 different careers as we're going through this cloud computing thing. So watch it again, read things that you're not, and you're going to be great. We all start as beginners, every last one of it. I wasn't born knowing how to practice medicine. I promise you that. And I definitely was not born knowing architecture. So thank you all. It's been an honor to spend the afternoon with you.